Hi guys, my name is Rishane. I'm one of the directors of Luminosity. Before we start the lesson, I just wanted to quickly go through some rules for the class. So if you can please just keep your microphones on mute. If you have any questions, you can raise your hand or just post a message in the group chat. The moderator will be reading those messages, and we will try to address any questions that you have. We may ask you to unmute your microphone. We are recording the lesson, so if you want to review some of the information in this lesson, we will give you access to that after the lesson. All right. Before we start, I just wanted to introduce who we are as Luminosity, what we do, and give you a bit of background on our tutors that will be taking you through the lesson today. So we're a tutoring company, and we try to focus on preparing you guys for examinations. So we do different courses. So this is our website, luminosityacademy.com. We do grade 11 and grade 12 exam preparation. This covers mainly maths and English. We also do SAT preparation. So for those of you that don't know, if you guys want to apply for a course in America, apply to one of the American universities, they have a standardized test that you're required to take in order to apply for courses in American universities. So we've got a preparation course for that. There is some overlap between the grade 11 and grade 12 examination course and the SAT prep course. So if you're in grade 11 and grade 12 and you take our grade 11 course, you can always upgrade to the SAT prep course, if you're considering applying to overseas universities. We also have a GMAT and GRE prep course. So this is for mainly for later on after you've got your degree and you want to apply for master's degrees overseas. We have courses that will help you prepare. So you might be thinking, well, what's different about Luminosity than any YouTube videos that you might watch? So if you guys have ever tried to research something on YouTube, I'm sure you might have spent more time actually trying to find the right video or the right information than you actually do learning something. So with our course, we have a whole video library that you can access to cover every section that's covered in the exam. And these videos are ordered in the order that you need to go through them to make sure that you have a good foundation, and then you build on that as you go. We also do things that you might not be able to get in the classroom. So teachers have limited time, so they can't go into detail about the foundations, and with especially subjects like maths, you need to have a strong foundation in order to understand the concepts. If you don't understand certain prerequisites, it's very difficult to understand the additional information that builds on those prerequisites. So we try to make sure that we cover all of the foundations. So even going back down to grade 8 concepts sometimes, just to make sure that we fill in all those gaps that might have been left in previous years, so that you guys can feel comfortable with what you're learning. We also try to make the information relevant as well. We try to take a storytelling approach to the way we teach. We try to put the knowledge in context to make you understand that these are tools, and these tools were developed for specific purposes and how they can be used. And I think that that's a far better way to learn a concept than just memorizing formulas. So we have the video library that goes into detail. Then we have live tuition sessions. So the live tuition sessions, after you've watched the video courses that are required for a specific topic, we have a live lesson each week for that specific topic. And that's where we do troubleshooting. So as you go through those video lessons, you might be struggling with certain sections. So in our live tuition sessions, you can ask all of your questions to the tutor, and the tutor will work through it. And we work through exam questions as well. So we have a lot of practice questions, and they come in different formats. We have quiz quizzes that you can do by yourself through our learning management system. When you log in, as you go through the videos in each section, you can attempt the quiz, and that'll give you an indication about how much of the content you actually understand. And then we also have the live tuition sessions where you can ask your questions there. And we also have videos that will go through specific exam questions in detail, so that you understand how questions should be answered. Because that's the other thing that you won't get with just researching things on YouTube. The videos might cover certain topics, but in the exams you may need to answer questions in a specific way using specific terminology. And we will teach you that to make sure that you answer the questions in the right way in order to get the marks that you need. All right, so that's a basic overview of what we do. If you want to sign up for a course, you can fill in our form. If you sign up before the 20th of December, you will get a discounted rate. So yeah, our prices will increase next year. And the other thing is, I just wanted to introduce our tutors for today. So for today, Fabian Palmer and Dan Govender will be taking you through the trigonometry section. So Fabian he has a Bachelor of Science and honors in pure mathematics, applied mathematics. Been tutoring for 9 years. Very talented tutor. And we've also got Dan Govender. He's got a Bachelor of Science in Biomedical Engineering and a Master's in Engineering Management. He studied in the US, and he's got a lot of experience, 14 years of experience tutoring students and preparing them specifically for SAT and advanced program, advanced placement exams. So yeah, these guys know what they're doing. They're very passionate about the subjects they teach. We always try to find the best tutor. So yeah, I hope you'll enjoy the lesson, and I'm going to hand over to Fabian first to take you through the content.
Cool. Well, good morning to everyone that's joined. So my name is Fabian. Thanks for the warm welcome, Roshan. Before I get started, I just wanted to give a warm welcome to all the participants for today's webinar. So welcome Kyle, Unati, Vida, Shamin, and Prashant. So welcome to the Trigonometry Webinar. In this webinar, we're going to aim to go over as much as possible on the following topics. So I'm going to start off with a brief introduction and history of trigonometry. We're going to revise the basic ratios, so sine, cos, and tan. We're going to be looking at constructing special angles, so the special angle diagrams. I'll be talking through the cast diagram, which is very important for your trig functions. And then we'll go into an interlude with some applications on trigonometry. And then for the remainder of the webinar, we'll be discussing the sine, cosine, and tangent functions. All right, so let's get started with that. Okay, so a brief history of trigonometry. Okay, so this is what I like to do in all my mathematics lessons. I'm a mathematician by heart, so I like to understand the history and where these things actually came from, rather than just giving you a list of formulae straight away. Okay, so trigonometry is a branch of mathematics, and if we break up the words trigon and nometry, it's Greek for tri, three, right? So your triangles, and metry was that geometric study of the three-sided shape. So starting off with your triangles, and that's where trigonometry really starts from, is analyzing the right angle triangle first of all, and then listing some properties, right, of that right angle triangle that we can use to define sine, cos, and tan. And we'll see later on how we actually generate the functions sine, cos, and tan from those ratios using something called the unit circle. All right, so what is a brief history of trigonometry? Well, trig dates quite a few thousand years back, around ancient Greece and ancient Babylonian and ancient Egyptian times. So in Egypt, they used trigonometry, and we'll see an application as well, to build and construct the pyramids. Right, so trigonometry had early roots starting off there. The Babylonians also had their form of trigonometry, which they inscribed in tablet forms. So we actually could see Pythagorean triplets. And we know Pythagoras is very famous in trigonometry because of the right angle triangle. They actually had values of Pythagorean triplets thousands of years ago already. So the 3, 4, 5 triangle, as we all know so well, that was known way, way long ago. All right. The major use of trigonometry really started with ancient Greeks, and they used it for astronomy, as we'll see in one of the applications as well. So looking at distances between different celestial objects, like stars and planets. So if you ever go into a field of astronomy or astrophysics, you will definitely have a good amount of trigonometry there to back you up. Right, and then trigonometry has grown since its early stages, and it's used in a lot of different places, right? Sound waves in sound engineering, also in electrical engineering, brain scans when you getting an MRI, for example. They all use aspects of trigonometry. So it's important to understand the basics of it and how we actually use it in order to do some more advanced stuff. All right, so that's just a little brief history of trigonometry. Let's go over where trig starts. Okay, trig comes all the way down to here, the right angle triangle. Right, this is your best friend in trigonometry because this is where we define those trigonometric ratios. Okay, so some of you might have seen this little acronym or mnemonic device called SOHCAHTOA, right? Essentially what it just does is just shorten what the trig ratios are actually saying in a right angle triangle. So if we look at this first one here, okay, well, how do we define the sine of an angle inside of a right angle triangle? So here's my angle theta, all right? So if I look at that angle theta and I ask, well, how do we define sine in that triangle? Well, we define it as the ratio, and that's a key word here, ratio, right? That's a fraction here, of the opposite value of that angle. So if I look at the opposite angle and I go in that direction, this would be the opposite length here, okay? And then in any right angle triangle, the hypotenuse is always the longest side, right? And that's always opposite the 90 degree of your right angle triangle. So to define the sine of an angle, we simply take the ratio, the opposite length, divided by the hypotenuse length. And we'll look at an example in the next slide just to see how we work that out. Similarly, if I take that angle theta and I now wanted to measure the cosine, okay, so cos is a short abbreviation for cosine, and we'll actually see later on when we do trig functions why the word co is suddenly in front of there, right? They were pretty smart when they were naming them, right? So cos of an angle theta is the adjacent side. So adjacent in normal English just means standing next to. So if I look at this angle theta, there are technically two sides that angle is standing next to, right? It's standing next to this side here, and it's standing next to this side here. But that side, the longest side, is always the hypotenuse of your right angle triangle. So the adjacent side is the other side that angle sits right next to. Okay, so the adjacent side of theta would be this length here. So we take that length and we divide it by the hypotenuse length. Okay, and that'll be the cos of an angle theta. And then lastly, tan of theta is defined as, from this angle, we go the opposite length, which is over here, and we divide it by the adjacent length, which is over here. Okay, and tan has a very nice identity because we actually see that it is sine over cos, and we can actually see that. So if I did sine theta, which we know from defining it here is opposite over hypotenuse, and I look at cosine theta, which is here, which we defined earlier, so cos of theta is adjacent over hypotenuse, then if I divide those two values together, so let's look at that in another color, let's put blue. So if I put sine theta over cos theta, let's actually see that the identity is true, right? Let's actually see that it gives us tan theta. Well, sine theta was opposite over hypotenuse. Okay. All right, so that's your numerator. And then you're dividing by cos of theta, which was adjacent over hypotenuse. Okay. So if I divide those two fractions, so yes, some algebra now involved. Remember, when you divide two fractions, the numerator, so there's it over here, opposite over hypotenuse. And because we're dividing by a fraction, we multiply by the reciprocal, right? So what does that mean? We tip and turn. So in this fraction here at the bottom, that becomes hypotenuse over adjacent. All right, so hypotenuse will cancel out in their multiplication, and we are just left with opposite over adjacent. And isn't that how we defined tan of theta initially? All right, so we actually see that the identity holds true, that tan theta can be written as sine theta over cos theta. Okay, so that was just revising some of the basic trigonometric ratios, sine, cos, and tan, right? And these will be super important when we go on to define how to draw the functions. Okay, so I'm going to move on. And while I'm busy doing this, just again, another warm welcome to everyone that's just joined now. Thank you for joining the Trig webinar, and we're going to be continuing here. Okay, so let's have a look at some examples of calculating sine, cos, and tan. So you can see that I've got three right angle triangles here, because this is how I'm going to work with sine, cos, and tan. Okay, so if I look at this first triangle, here's the angle theta here. If I wanted to work out sine of theta, okay, I would need the opposite length over here, okay, so that's my opposite length, and divide it by my hypotenuse. My hypotenuse is always opposite the right angle, so my hypotenuse is 5. So sine of theta is equal to opposite, which is 3, over the hypotenuse, which is 5. Okay, so that's calculating sine theta. What about cos theta? So let's have a look at that. Cos theta says I'm going to take the adjacent length, which is this length here in green, and divide it by the hypotenuse length here. But I've already run into a stumbling block now. I don't have that missing side, but I can work it out, right? And this is why Pythagoras is so powerful in trigonometry, because of the right angle triangles. All right, so I can use Pythagoras' theorem here, which says that in a right angle triangle, if I take the one length and I square it, and I add it to the other length and square it, then it should be equal to the square of the hypotenuse. So in this case, if I let my adjacent side equal x, then I can use Pythag. So let's use some Pythag here. Right, so I know my adjacent length x, if I square it, and I add it to the square of the opposite side here, 3, so 3 squared, that must equal the hypotenuse squared, 5 squared. Okay, I can now solve for x squared, so let me simplify. 3 squared is 9, and 5 squared is 25. And I'm performing algebra here, so I need to solve for x. I'm going to move this plus 9 over to the right-hand side. So how do we get rid of plus 9? We do the opposite operation. So the opposite of addition is subtraction. So I'll subtract 9 on both sides. So I get 25 minus 9, which is 16. Now, this is where a lot of students will fall wrong, okay? This is an algebraic equation with x squared equals 16. So algebraically, when you square roots, you do expect a plus or minus solution. So it'll be plus or minus the square root of 16, which is plus or minus 4. Okay, that's correct algebraically. That's how you would do it if you were solving an algebraic problem. But because this is being applied directly to right angled triangles, we know that when we talk about lengths, we are talking about positive numbers. Okay, so we discard the negative, and that length here is 4. And that's the famous 3, 4, 5 right angled triangle, right? So now that I've got my adjacent side, I can now work out cos of theta. So cos of theta is adjacent, which is 4, divided by my hypotenuse, which is 5. Lastly, we can work out tan of theta. So what is tan of theta? Remembering that the ratio is opposite side, which is 3, over the adjacent side, which is 4. So the tan of theta in this right angle triangle is equal to 3 over 4. Okay, let's look at the next one. Again, you've got a right angle triangle, and your angle theta now is over here. Okay, so let's work out sine, cos, and tan of this triangle. Before we do that, you can see there's a missing side, the hypotenuse length. So let's go ahead and use Pythag to work that out first. Okay, so let's bust out our old friend Pythagoras here. Right, if this is the hypotenuse, let the hypotenuse be x. Okay, then we know that if I take the adjacent, the opposite side of theta, which is 5 here, so 5 squared, plus the adjacent length, which is 12 squared, that must equal the hypotenuse squared. Okay, so therefore, x squared is, well, 5 squared is 25, and 12 squared is 144. Okay, well, 25 and 144 added together will give you 169. And therefore, when you take the square roots, again, you do expect a plus or minus of a solution algebraically. But remember that you are looking at distances, okay, lengths in triangles. So it's a positive value. Well, the square root of 169 is 13. No, I did not just work that out very fast. I'm not a human calculator. That is a myth with mathematicians. Okay, we're not human calculators. It's just that these are very famous triangles. So these values pop up a lot. And as we practice them more and more, we actually see these values pop up a lot. And that's how we can quickly work it out. Okay, so if your math teacher ever pulls out a square root of a huge number very quickly, just know they've probably worked with that number quite a lot already. All right, so again, we discard that minus sign because it's a length. And my hypotenuse length is 13, which we can see is correct as well, because we notice some nice little properties of triangles, right? The right angle, which is the largest angle in this right angle triangle, is opposite the largest side of the triangle, 13. So if you had your hypotenuse, you worked it out to be, let's say 6 or 7, you know you've gone wrong somewhere, because there's always ratios in triangles. Opposite the hypotenuse should always be the largest side of your right angle triangle. Okay, we've got all the lengths now, so we can work out sine of theta. So here's theta. Opposite, it is 5 divided by the hypotenuse, which is 13. Let's have a look at cos. So cos of the angle theta is the adjacent side, which is 12, divided by the hypotenuse, which is 13. Okay? And then lastly, we look at tan of theta. So tan of theta, again, we know as the ratio opposite over adjacent. So I look at my opposite side, which is 5. Okay, so tan of theta is equal to opposite, which is 5, divided by my adjacent side, which is 12. Okay, so that is tan of the angle theta, 5 over 12 in this right angle triangle. All right, let's have a look at the last one here. So again, identify where's the angle I'm talking about, theta. It's over here. Because wherever that angle theta is, that's where you're looking in relation to the opposite side, the adjacent side, and the hypotenuse of that right angle triangle. Okay, so I have a missing side. I can use Pythag here to solve for that unknown side. So let's do that. Let's put you in a different color. So using Pythag again, we have the adjacent side of 4 squared plus, we don't know this missing side, so let's call it x. Okay, so 4 squared plus x squared, and that must equal the hypotenuse length, which is opposite the right angle, and that's 10 squared. All right, so now we have x squared plus, well, 4 squared is 16, and 10 squared is 100. The goal is to solve for x squared, so I'll subtract 16 on both sides to get rid of the plus 16. Okay, so 100 minus 16, that should be 84. And again, algebraically, when you solve this, when you take the square root, you do get a plus or minus. Okay, but because it's a length, you're looking at the positive value only. Okay, so that's square root of 84. Okay, and we can simplify that down, right? So we look for perfect square numbers that can go into 84. I think 4 is a good one here. So this is an example of how to simplify a surd now. So 4 goes into 80 20 times. right? And 4 goes into 4 itself once. So I say it's 4 times 21. Okay, and that'll give you 84. Well, 4 is a perfect square, and remember, because it's being multiplied, you can break them out. The root of 4 times the root of 21, and the square root of 4 is just 2 times root 21. Okay, so that is the unknown side here, 2 times root 21. Okay, so now we can use sine, cos, and tan to work out those ratios. So what is sine of the angle theta? So opposite theta is that unknown length there which we worked out, which was 2 root 21, over the hypotenuse, which is 10. And you can simplify that down more. So 2 goes into itself once, and 2 goes into 10 5 times. So it's square root of 21 over 5. All right, let's have a look at cos of theta. So cos of theta is the adjacent side, which is 4, right? Adjacent to the angle theta is 4 over the hypotenuse, which is 10, right? 2 can go into 4 2 times, and 2 can go into 10 5 times. So that is the value of cos of the angle theta in that right angle triangle. Lastly, let's have a look at tan of theta. And again, tan of theta is the opposite side, which is 2 times root 21. Okay, and we divide it by the opposite, so opposite over adjacent. So the adjacent side is 4. So we can simplify that down. 2 goes into itself once, 2 goes into 4 2 times. So tan of theta is the square root of 21 over 2. All right, so that's an example of just finding sine, cos, and tan in a right angle triangle. Okay, now we're going to move on to constructing the special angles, and this is where trig really starts to come alive. Okay, because these special angles are just seen everywhere. So it's important to understand how to construct your special angles from your special angle triangles. Okay, so the first one we'll start off with is the equilateral triangle. Okay, so let's just start with an equilateral triangle, and let's call all the side lengths x. Okay, these are all equal lengths because it's an equilateral triangle, and because it's equilateral, we know all 3 interior angles must be 60 degrees each, because the sum of these angles, right, 60 plus 60 plus 60, must give me 180 degrees. So that's the basic properties of your equilateral triangle. For simplicity's sake, as we go down, once we've worked it out, we usually let x equals 2, because that will be the default special triangle you usually draw when you want to construct your special angles. And we'll see that as we go through. So let's start off with that triangle. Okay. Let's drop a perpendicular bisecting line. So a lot of words going on there. In mathematics, you do see a lot of big terminology, but it's easier when you just break up each word to understand what it's saying here. So perpendicular line from this top point A down to here just means that it meets at right angles. That's all that means, perpendicular, right? And bisecting just means that as we land down here, we're cutting the lengths in half. So where the original length of BC was x, if I cut it in half, well then this length BD is half x, and this length DC is half x. So that's what perpendicular bisecting line just means. Okay, so you just break up each word and then put it into the diagram. And that's true for a lot of areas in mathematics, right? Especially in your circle geometry, because there's a lot of constructions that go on there. So this line also bisects the angle A. So where this original angle here was 60 degrees, it bisects, so it cuts the angle in half, 30 degrees here and 30 degrees here. So you can see you actually have 2 congruent triangles next to each other, right? So triangle ABD and triangle ACD are congruent, right? And they're congruent by which property, right? So they both have equal hypotenuse, right? So your hypotenuse are your opposite, your 90 degrees, okay? They both have a common side AD in length, okay? And we said that there was a 90 degree angle here between 2. So this is actually the congruency, right angle, hypotenuse, common side. Okay. So there's actually two congruent triangles next to each other here, so we just have to work with one of them, okay, to get our special angles, because in each triangle there's a 30 degree, there's a 60 degree, and a 90 degree, and this is where we're going to get our special our ratios for our special angles. So we can work out the length of that unknown side there, AD, that we've just constructed using Pythagoras. And again, in this right angle triangle, let's look at ABD, right? So this left one here. You can see that if I square this length here, AD squared, that's the side I'm looking for. We don't know that length, and that's what we want to work out. Well, if I square that and I add it to this side squared, so a half x squared, which we've got there in brackets, that must equal to the hypotenuse squared, which is that length there. Okay? So that's x squared on the right-hand side. So you can see the algebra coming out here. That's why you have to be consistent with your algebra when you're doing trigonometry, because that's what actually gets tested more often than anything, is your algebra within your trigonometry. Okay, so I'm still looking for AD squared. Keep your eye on the prize, right? That's the goal. We're looking for that length AD that we drop down, because when we have all three lengths, we can then work out sine, cos, and tan of those special angles, 30 degrees and 60 degrees. Okay, so AD squared, that's what you're looking for. Well, what is a half x squared? Remember that what you're saying here, a half x squared, means you're taking whatever inside the brackets, in this case a half x, and you're multiplying it by itself 2 times. That's what exponentiation means, right? When you have a square there, you're taking whatever in the brackets and you're multiplying by itself 2 times. If it was a cube there, you would take that same number and you'd multiply it by itself 3 times. Okay, so if I do that, a half and a half, if I multiply them, gives me a quarter, and x times x will give me x squared. And that's what I've got here on the left hand side. And then x, if I square that, just becomes x squared. Now the goal, again, keep your eye on the prize. You want to solve for AD. So I'm going to subtract this quarter x squared from both sides to get rid of it. So on the right hand side I have x squared minus 1/4 x squared. Well, these are like terms, right? They both have an x squared, and in front of the x squared here there's a 1, and in front of this x squared the coefficient here is a quarter, and we're subtracting those two. Well, how can I write x squared with a denominator of 4? Because that's how we add and subtract fractions, right? Well, I know that if I want to have it as a base of denominator of 4, I multiply this denominator here, which is 1, right? X squared divided by 1 is x squared. I multiply that by 4. That means I'll multiply the top by 4. So I get 4x squared. And then you're subtracting 1/4 x squared. So now that the denominators are equal, now I can do algebra on fractions. And again, this is where you got to be very careful whenever you do any algebraic operation, is to make sure that you are doing them correctly, especially in fractions. Okay, so now I can subtract the numerator values. 4 minus 1 is 3 x squared divided by that denominator 4. And that's what we have on the right hand side here. Lastly, I'm going to take the square root on both sides, okay, because that'll get rid of the square here for AD. And if I take the square root of 3/4 x squared, okay, because they're being multiplied, I can only do that when it's multiplication. I can take the square root of 3/4 first, and then multiply it by the square root of x squared, okay? Well, again, because there's division here now, and again, multiplication and division are the only times we can do this with surds, I can break up that to be the square root of 3 divided by the square root of 4. And that's how I get square root of 3 here in the numerator, and the square root of 4 in the denominator is just 2. And that's where we get the 2 here in the denominator. And then you're multiplying by the square root of x squared. That'll just give you x. So that's how we calculated the unknown length there using Pythagoras. And he will pop up a lot whenever we do right angle triangles. Okay, now that we've got all the lengths, we can now start working out sine, cos, and tan of 30 and 60 degrees, which are our special angles. So let's look at 30 degrees highlighted over here. If I wanted to do sine of that angle, okay, I look at the opposite length, which is BD, and that has a length of a half x. So that's what I have in my numerator. Then I divide it by the hypotenuse, which is AB, but that has a length of x. So this x in the numerator will divide with the x in the denominator, and what you're left with in the numerator is just a half, which is divided by 1, which still stays a half. Okay, so that's the sine of 30 degrees. Okay, so the sine of 30 degrees, which is your first special angle you learn, is a half. So that's where that comes from. What about cos of 30 degrees? Well, to work out cos of 30 degrees, again, I use one of the ratios we defined. So it's the adjacent side to 30 degrees, which is the length AD, which is here, root 3 over 2x. So that's what I have in my numerator. And I divide it by my hypotenuse, which is the denominator here, which is x, right? The length AB. So the x's will divide into each other, right? So you're just left with 1 in the denominator. And you have root 3 over 2 divided by 1, which is just root 3 over 2. So there's your next special angle. Cos of 30 degrees is the root 3 over 2. Lastly, what is tan of 30 degrees? So tan of 30 degrees is the opposite length, which is BD, which is a half x. That's what you have in your numerator. And you divide it by your adjacent side, which is AD, which is root 3 over 2x in your denominator. The x's will divide into each other. And now look at this. You have, okay, so I've written it like this. So it's a half x in the numerator. And now because there's a fraction in your denominator, you multiply by the reciprocal. So the numerator part here is root 3x. That becomes the denominator. And the denominator part here was 2. So that becomes your numerator. So if I multiply those out, the x's will divide into each other. The 2's will divide into each other. And now you have 1 over root 3. But we don't like to have surds in the denominator. So we use a technique called rationalizing the denominator, which you will do in algebra. So you multiply both sides, the top and the bottom of the fraction, by that surd, root 3. Okay, and in doing so, the numerator becomes 1 times root 3, which is just root 3. And the denominator, well, root 3 times root 3, right? You can bring those 3's together in because it's multiplication. So it's root 3 times root 3, which is the root of 3 times 3, which is just the square root of 9. Okay, which is 3. The other way you could have seen that is root 3 times root 3 is just root 3 squared. And the square roots undo each other. Okay, so that is the ratio of tan of 30 degrees. The square root of 3 over 3. So whenever you have special angles that you work with, and you will work with special angles a lot in your trigonometry, it's very, very crucial to know the special angle triangle. Okay, and how it's usually drawn in practice, right? Because you don't need both sides. You just draw one right angle triangle, okay, with a 90 degree, a 30 degree, and a 60 degree, okay? And we know the ratio lengths, we've worked them out, okay? So sine of 30 is opposite, which is 1, over the hypotenuse, which is 2. And if you use Pythagoras here, we get that length to be square root of 3. Okay, so that is the special angle triangle that we usually draw once we understand this one here. Okay, and that'll give you all the correct values here. So sine of 30 is opposite, which is 1, over hypotenuse, which is 2. Okay, cos of 30 degrees is the adjacent side, which is square root of 3 over here, divided by the hypotenuse, which is 2. So we get those values. And then tan of 30 is opposite, which is 1, over adjacent, which is root 3. And again, we don't like to write surds like that, so we rationalize it, right, by multiplying the top and bottom by that root 3, and we get root 3 over 3. Okay, so that is for 30 degrees. Let's have a look at 60 degrees. So now here's the angle of interest here, okay, in that one triangle. Okay, well, what is the sine of 60 degrees? So again, we follow the ratios that we defined. The sine of 60 is the opposite length, okay, which is root 3 over 2x, and we divide that by the hypotenuse, which is AB, has a length of x. Okay, so in your numerator, you have root 3 over 2x, and your denominator you have x. So the x's will divide, and you see it simplifies down to root 3 over 2. So while I'm doing all of this, you can see why I first started off with just letting the length be x instead of, like I said at the end, we'll let it be equals to 2 for simplicity. It's because I could actually have x being any value here. It could be 10, 50, 1,000, a million, anything. Okay, but in a 30, 60 degree right angle triangle, the ratios of sine, cos, and tan will always simplify down to these fractional values that we're writing here. Okay, so that's the beauty of the special angles, that no matter what the lengths are of your equilateral triangle that we've drawn here, the ratios of sine, cos, and tan for the angles will always simplify down to these simple ratios. Let's have a look at cos of 60 degrees. Well, again, the adjacent side to 60 degrees is BD, which is a half x. That's what we have here. And we're dividing that by the hypotenuse length, which is AB, which is this length x here. All right, so the x's will divide into each other. So you have a half divided by 1, which is just a half. Okay, so that is the cos of 60 degrees. And lastly, tan of 60 degrees, again, we use the ratios we defined. It's the opposite length, which is root 3 over 2x, divided by your adjacent length, which is a half x. And again, I'm dividing by a fraction here, so algebraically I have to be so careful the way I do this. Okay, because when I divide by a fraction, I'm multiplying by the reciprocal of that fraction. So the denominator 2 here becomes 2 in the numerator when I multiply. And the 1 times x in the numerator becomes the denominator now. So now that I'm multiplying the two together, the x in the numerator there will divide in the x in the denominator there. These 2's will also divide into each other, and you have the square root of 3 divided by 1, which is just the square root of 3. And that'll give you the tan of 60 degrees. Okay. So we will see at the end in a summary how all these angles look for 30 degrees, 60 degrees, and the next special angle that we're going to talk about, which is 45 degrees. So how do we do the 45 degrees triangle? Well, this is a nice one. You start off with an isosceles right angle triangle. So again, a lot of words, we break them up to understand what's going on here. So isosceles just means that two sides must have equal length and equal corresponding angles. In this case, AB and BC are x and x here. Okay, and again, we'll let x equals 1 at the end just to simplify the values down. So with these corresponding equal lengths, we have 45 degrees and 45 degrees because those will add up to 90 degrees. And then you have a 90 degree here, so that all adds up to 180 degrees. So this is a correct triangle, right? The angles sum up to 180 degrees. All right, now that we've got that triangle, we can start working out sine, cos, and tan of 45 degrees. Okay. So let's first work out the length of that hypotenuse, right? And again, our friend Pythagoras pays us a visit, right? And he asks us to solve the unknown length here. So if I use Pythagoras, it is the adjacent side here, x, which is AB, so x squared, plus this opposite side here, BC, which is also x, so x squared. And that's equal to the hypotenuse squared, AC. Okay, so here's the equation here. We have x squared plus x squared. They are common terms. They are both x squared, so I can add them together. Again, being very cautious of my algebra. So 2x squared, and that's equal to AC squared. So keep your eye on the prize. You want to solve for AC. So I'll square roots both sides. And if I do that, again, because it's being multiplied, I can separate the square roots out. So it becomes square root of 2 times the square root of x squared. Well, the square root of x squared, right, those will cancel each other out. So you're left with x, and the root 2 just stays root 2 by itself. So that's that unknown length there, AC, the hypotenuse that we just worked out. The square root of 2 times x. Now that we've got all four sides, not a quadrilateral, it's a triangle, all three sides, we can work out sine, cos, and tan of those special angles, in this case 45. So sine of 45 degrees. Okay, so if I look at this 45, I could also look at this one here and I'll still get the same values. Okay, so if I look at this one in blue, opposite length is BC, which is x. We've got that in our numerator. Then I divide it by the hypotenuse value, which is square root of 2x. That'll be in your denominator here. The x's will divide into each other, and you're left with 1 over square root 2. Again, we don't like having surds in the denominator. So how did I correct this? Well, I said 1 over root 2, and I multiplied the top and bottom by root 2. You ask yourself, why can you do this rationalization technique? Why does it work? Well, root 2 over root 2 is equal to 1, right? Any number divided by itself, except 0, is equal to 1. So if you're multiplying a number by 1, are you changing that number, right? So like 10 times 1, that's still 10. You're not changing the number. So that's where the technique of rationalization comes from, to get rid of those surds in the denominators. Okay, so our little algebra excerpt aside, that becomes 1 times root 2 in the numerator, which is root 2. And then root 2 times root 2 is just root 2 squared. And the square and the square root will cancel each other out. And that's how I get that root 2 over 2. And that's how your calculator also gets root 2 over 2 when we look at the values, when we punch in sine of 45. Let's see if I'm just talking nonsense or not, right? Let's pull up a calculator and actually just check, right? So let's just pull that one down a bit. There we go. Okay. Cool. So if I did sine of 45 degrees, and my calculator is in degrees mode because of the D on top there. Usually by default, your calculator stays in degrees mode. Some of you might ask, sometimes you might see your calculator with a capital R. That stands for radians, right? And you'll only ever use that when you're doing AP maths or first year level maths at university onwards, because that's when they deal with radians. But we deal with degrees. So sine of 45 degrees, and you can see your calculator tells you root 2 over 2. Okay, and that's where your calculator is very smart in that it's rationalizing 1 over root 2 for you. That's what it's actually doing. Okay, so that's how we got that value for sine of 45. If we do cos of 45 degrees, okay, again, I look at the ratios. It's adjacent, which is AB, which has a length of x, and I divide that by the hypotenuse, which is AC, the square root of 2 times x. So again, the x's divide into each other, so you're left with 1 over square root 2. And then again, similar process, we rationalize and we see that we get root 2 over 2. So that's pretty interesting. The sine and the cos of 45 degrees are equals to each other. And this is where I really love mathematics and spotting patterns, because that is not a coincidence. There's actually a reason for that, and we'll see it when we go on and we do the unit circle and how the angles match up. So the last one is the tan of 45 degrees. And this is a very nice one. Okay, so this one here is opposite length, which is BC, which is x, divided by your adjacent length, which is AB, which is x. Well, again, x divided by x, a number divided by itself is equal to 1. All right, so tan of 45 degrees is equal to 1. Knowing these special angles doesn't just help you in trigonometry, because when you do analytical geometry, you'll see that you also use tan of theta when you talk about the gradient of a straight line. And knowing your special angles will also help a lot, because tan of 45 degrees equals 1, well, that could be a gradient of a straight line equation. Okay, so you can see that trig doesn't stand by itself. It's used in many other fields of mathematics that you'll study. Okay, so let's have a look at the summary of the special angles that we've worked out. Okay, so for sine of theta, okay, for 30, 45, and 60 degrees, these were the values: a half, root 2 over 2, and root 3 over 2. And I see a little pattern here. All of them have a denominator of 2, and you can sort of see it's like a 1, 2, 3, but there's a square root of 2 there, square root of 3 there. I mean, you could say square root of 1, right? Because square root of 1 is 1. So that's like just like a nice little pattern to see across sine, right? For 30, 45, and 60, which are your special angles. So if you go across, they all have a denominator of 2, and the numerators are root 1, root 2, root 3, which I think is like a nice way. There's a lot of mnemonic devices of being able to recall the special angles quickly. Okay, so there's the table form here. Drawing your special angle diagrams is another mnemonic device that you can use to work out your special angles like we've done. Cos of theta, if I go in the order of the special angles 30, 45, 60, also has a very similar pattern. They all have a denominator of 2, but you see this time it's going backwards. Root 3, root 2, and you could say 1 is just root 1 if you wanted to, right? Which is square root of 1 is just 1. So there, the cos pattern looks like it goes backwards to the sine pattern, which is pretty cool. Then tan of theta, how I find these values very quickly, I just recall that the identity sine of theta over cos of theta is equal to tan theta. So if I do that, if I take sine theta and I looked at this value here, a half, and I divided it by this cos value, root 3 over 2. Well, if I look at the pattern really carefully, if I just look at the numerator here, 1, and the numerator here, root 3, I can actually just write it as 1 over root 3. Okay, and again, we rationalized that and we saw it as root 3 over 3. Same for 45 degrees. If I just, because tan is sine over cos, if I just look at the numerator sine here and the numerator of cos here and I divide them, well, root 2 over root 2 is equal to 1, right? A number divided by itself is 1. And lastly, for tan of 60 degrees, if I just look at the numerator here and the numerator here, root 3 over 1, that just gives you root 3. So that's a quick way, a nice mnemonic way in a table format to write down your special angle values. All right. So these are very important because we use them all the time when we construct not just right angle triangles, but when we draw the sine, cos, and tan graphs, when you go on to solve more complicated problems in trig equations and trig identities, your special angles just pop up everywhere. That's why it's so important to actually understand how to get your special angles. Okay. Let's have a look at an example using the special angles. Okay, in the first triangle, I have the sine of 30 degrees. Sorry, I have 30 degrees. I'm getting ahead of myself, sine of 30 degrees. We want to find the unknown value of x, and I kind of gave it away already, right? X is opposite the length of 30 degrees. And you have your hypotenuse, which is opposite your right angle, with a value of 10. So if I had to pick one of the trig ratios, sine, cos, or tan, I would probably pick sine here, because I have an opposite value already, and I have a hypotenuse value. So I would say the sine of 30 degrees is equal to opposite, which is x, over hypotenuse, which is 10. So therefore, if I wanted to solve for x by itself, because it's being divided by 10, I multiply both sides by 10. So 10 times sine of 30 degrees is equal to x. Okay, but I know what sine 30 degrees is, thanks to my special angle diagrams, right? It's a half. So therefore, x is equal to 10 times a half, which is 5. So that unknown side there is 5. And you can see when I started right at the start there, when I said for simplicity's sake, we'll let x equals 2, and then for the other one, let x equals 1. The reason why I said that is because x could be any value. So you could see here, I have 5 over 10 in this right angle triangle, but we are used to working with the right angle triangle that has 1 over 2 for 30 degrees. Okay? But can you see the ratio always simplifies down? Because you have sine of 30 is opposite, which is 5, over the hypotenuse, which is 10. Well, 5 divided by 10 is just a half. It simplifies down. Okay, so that's what I was mentioning about, you know, for simplicity's sake of using an x value of 2 or x value of 1 when you draw your special angle diagrams. It's just because the ratios will always simplify down to these nice values that we've worked out. Okay, let's have a look at this one. We have a 45 degree, and we have a length that's adjacent to the 45, and we have the unknown value x being opposite the 45. So I think of my 3 trig ratios, and I think which one has an opposite side and an adjacent side that I can use. Well, sine and cos both work with hypotenuse, and we don't know what that is. So it's tan that we're going to use here. So tan of 45 degrees is going to be the opposite length, which is x, divided by your adjacent length, which is 3. Again, I can solve for x here, do some algebra. You're dividing by 3, so we can multiply both sides by 3. So 3 times the tan of 45 degrees equals x. But thanks to my special angle diagrams, I know that the tan of 45 degrees is 1. That's what we just worked out earlier. So x is equal to 3 times 1, which is 3. And again, when we did the 45, 45, 90 triangle, right, again, regardless of what the lengths are, we remember that when we did tan of 45 degrees, okay, so in the special angle diagram that we drew, 45, 45, and 90, our lengths here were, we said 1, 1, and root 2, okay? So tan of 45 degrees, if I look here, is this opposite side, which is 1, divided by this adjacent side, which is 1. So 1 divided by 1 is 1. And again, here, if I look at this bigger triangle, tan of 45 is opposite, which is 3, divided by the adjacent, which is 3. While 3 divided by 3 is still 1. So you can see that the values still simplify down to that most basic ratio that we worked out in the special angles, regardless of the lengths of that right angle triangle. It's all about the angles. So when you see a 30, a 45, or a 60, you know you're going to use your special angles. Lastly, I have a 60 degrees here. The opposite side to 60 is unknown. So I'm probably not going to use sine, because sine has an opposite inside of it. I have an adjacent value, and I have the hypotenuse value. So I'm probably going to use cos here. So I could say cos of 60 degrees is the adjacent side, which is 6, divided by the hypotenuse length, which is x. So remember, you want to solve for x here. So to get rid of x in this denominator, I'm going to multiply both sides by x. Okay, so you have x times cos of 60 degrees equals, well, the x's will divide into each other, and you have 6. Cos of 60 degrees, I go back to my special angle diagrams, and I know cos of 60 is going to be a half. So you have an x times a half equals 6. To get rid of that half, we multiply both sides by 2, right? Because 2 times a half will get rid of that half. So if I multiply by 2 on the left, I have just x. And if I multiply by 2 on the right, I'm going to have 6 times 2, which is 12. And again, that makes sense in this triangle, because opposite the 90 degrees should be the largest side. So here you have your unknown length to be 12. That is the hypotenuse length. Okay. Next, I just want to discuss the cast diagram, because again, this cast diagram is going to be able to tell you where your sine, cos, and tan ratios are going to be positive or negative numbers. And this is very important when you do things like your reduction formulae, and when we solve, when we look at the sine and cos waves, we'll see how they go from positive to negative, depending on the angle that we are looking at. Okay, so what is the cast diagram? The cast diagram is just a nice diagram that allows us to label where the ratios sine, cos, and tan will be positive or negative. Okay, and we'll start off in the first quadrant. So when you work with your Cartesian plane in normal geometry, in analytical geometry, you have your x and your y axis. Okay, you are still using the Cartesian plane when you do trigonometry. Okay, but we are more interested in the angles now that a straight line makes with respect to this positive x-axis here. Okay, so that's the convention. So from the positive x-axis, if we measure an angle theta, and we look at the line that meets that angle theta, okay, we can then discuss sine, cos, and tan of that angle. Okay, and we can see that this angle is going to be between 0 degrees and 90 degrees. Okay, and we call this patch here in the top right of the Cartesian plane the first quadrant, or quadrant 1. Okay, and in any trigonometry that we do, the convention we've chosen is to always measure angles from the positive x-axis, and we go in an anti-clockwise direction. So we go this direction, anti or counterclockwise, however you want to call it. Okay, so it's just going the opposite side that a clock would usually go. So a clock goes from 1, 2, 3, 4, 5, 6 o'clock, right? So it's going in a clockwise direction. But we measure angles, positive angles, from the x-axis to a counterclockwise direction. If we measured angles going this direction now, okay, we're still measuring angles, but now we're measuring the angles in a negative direction. So this could be, for example, negative 60 degrees. If you measure it from the x-axis and you swing downwards, okay, or swing clockwise rather. Okay, so but for convention, we always measure positive angles anti-clockwise. So let's have a look at this diagram. In the first quadrant, I've labeled it A. Okay, and A stands for all trig ratios in that first quadrant are positive. And we can actually see why. Again, you have a right angle triangle if you drop a perpendicular line here to the x-axis. And we define sine, cos, and tan in terms of ratios. So sine of theta is the opposite value, right, which just has a length of y. Not just y, but positive y, because it's on the positive y-axis. Divided by your hypotenuse length here, which I've called r. And there's a reason why we call it r. It stands for radius, because we're going to see that we can generate a circle, right, which will have a radius, which will be the hypotenuse. And that circle will actually generate the sine and cos waves for us. And radius is always a length, so it's always measured as a positive value. Okay, so you have positive divided by positive, which is just going to give you a positive number. So the sine of any angle between 0 and 90 will be positive. So for example, if I took sine of 15 degrees, that's in between 0 and 90. And if I look at my calculator, I should get a positive value. Sine of 15 is 0.258, which is still a positive number. Okay. Similarly for cos, okay, remember cos from that angle is the adjacent value, which is an x value here. It could be 3, 7, million, but as long as it's an x value on the x-axis here. We also know that this x value, this length here, is going to be positive because it's on the positive x-axis. So you have a positive number over the radius, which is always positive. So you end up with a positive value. So if I took, let's say, cos of 23 degrees. 23 degrees is between 0 and 90. So I should expect a positive number based off the ratios here. So cos of 23, 0.92, which is a positive number. Okay. And lastly, tan of theta, we measured as the opposite side, which is a y value, which is positive, divided by the x value, which is also positive. So again, positive divided by positive is positive. So if I took tan of, let's say, 49 degrees, that's still between 0 and 90. We should expect a positive value. So tan of 49, 1.15, which is a positive number. Okay, so that's the first quadrant in your Cartesian plane for the cast diagram. So A is in the first quadrant. Let's go to the second quadrant. Okay, because you can see we're moving anti-clockwise again. So now we're in the second quadrant where the angle is between 90 degrees, so from this axis here to 180 degrees. So that's the whole second quadrant's angle between 90 and 180. Okay, but if you look at that, yeah, you can see that your radius value is still always positive. Your y value, so the opposite of this angle theta. Okay, so theta is not here. Okay, theta is the angle from the positive x-axis measured all the way to that line. So again, opposite that theta will still be this y value here, that length there, which is positive, okay, because it's on the positive y-axis side. But look at your x now. Your x coordinate is sitting here on the negative x-axis. So your x value is negative. It's less than 0. Your y value is still bigger than 0, and your radius, your hypotenuse length, is always a positive number. Okay. So we say sine is the only positive trig ratio in quadrant 2. And let's look why. Because sine of theta is y over r, right? Opposite over hypotenuse. And they are both positive values. So I get a positive number coming out of there. Cos of theta now is a negative value, the x value, adjacent, divided by the radius, which is always positive. So negative divided by positive will give you a negative number. So cos of theta in this quadrant should be negative. And tan is opposite, which is y, divided by adjacent, which is x, which is a positive number divided by a negative number, which should always be negative. So let's test that quickly. Let's take our theta angle here to be 128 degrees. That's between 90 and 180. So let's see if sine is positive first. So sine of 128. I get 0.78, which is positive, okay? If I take cos of 128, I get negative 0.61. Okay, so now I can see that cos is negative in that quadrant. And if I take tan of 128, I get negative 1.28 rounded off. And that is a negative value. So the cast diagram is telling you in your second quadrant, when you have an angle measured that is between 90 and 180, only sine of that angle will be positive. Okay, cos and tan will be a negative value. Okay, in the third quadrant, again, moving anti-clockwise. Okay, so your third quadrant is between 180 and 270 degrees. Right, tan is the only positive trig ratio here. And let's have a look why. Well, can you see the adjacent value to this big angle theta measured here is on the negative x-axis side. Okay, and your y value is also measured, right? The opposite length is now in the negative y-axis side. So both your x and your y values are less than 0. So again, if I use sine, cos, and tan by looking at the ratios, I can see sine is going to be a negative answer, cos is going to be a negative answer, and tan will be a positive answer. So it'll be a negative y value over a negative x value. So let's take a theta value. Let's call it 212 degrees. Okay, that's between 180 and 270. Again, we can see sine of 212 degrees is going to be negative 0.53 rounded off. That's negative, and that's what we expect sine to be in the third quadrant. Cos of 212 degrees, negative 0.85 rounded off. Again, that's what we expect in the third quadrant. Cos will be negative. But tan, we expect to be positive in this quadrant. So tan of 212, 0.62. So it's a positive number. It's still a positive number. Okay, so tan is only positive in the, the only positive ratio in the third quadrant will be tan. So sine and cos will be negative. And lastly, in the fourth quadrant, C in the cos diagram stands for cos, is the only positive trig ratio. And again, if you look at this big angle theta measured here, the adjacent side x is now on the positive x-axis. The opposite value y is now on the negative y-axis, and your radius is always positive. So again, looking at sine, cos, and tan, we can see that the only time it'll be a positive ratio is when you look at cos. Again, I'll take an angle between 270 and 360. Let's say 325 degrees. That's between that. Now we only expect cos to be positive here. So if I take sine of 325, that's going to give me negative 0.57. So you can see it's negative in that quadrant. If I take cos of 325, I should expect a positive answer. Positive 0.82 rounded off. Okay, and then tan, I should expect a negative answer. So tan of 325, negative 0.7. So the cos diagram will be able to tell you correctly when you're measuring angles if it should be a positive or negative value in that sine, cos, or tan ratio. Okay, so that's the helpfulness of the cos diagram, to tell you what the sine will be, and then also to do your reduction of your angles. Okay, so we're going to take a bit of a break from the theory now, just talk a bit about some applications of trigonometry. And then once I'm done with that, I'll be handing over to my colleague Dan, who will be taking us through how to generate the sine, cos, and tan functions using the unit circle. And then we'll do some examples on trig functions to end it off. So trigonometry, like I said, is used in various fields of maths, and not just in maths, but in other fields like physics or biology. And they solve real world problems, okay? So here's just a short list of some of the applications. We won't get into too much detail with these, but on the last example, I'll go into a bit of detail and show you how you can actually use trig in a real world problem. So the first one, starting with something called the theory of parallax, right? Which sounds like it should be in a sci-fi movie, which is not far off because it has definitely something to do with science, right? So like I mentioned, trigonometry had its roots beginning in astronomy, and the ancient Greek mathematicians would calculate distances between celestial objects such as stars and planets using trigonometry. And what they called then the theory of parallax was just measuring distances between objects using right angle triangles. So for example, a very rough example, you could have the planet Earth here, right? And then you could have some distant star here. Okay, it's like the most rudimentary drawing of a star there. But you could, in theory and astronomy, use trigonometry right, and what they called then the theory of parallax, to work out the distance between celestial objects. It gets a bit more involved, but knowing your basic trigonometry ratios is the key to start off learning how to calculate distances like that. So if you ever go into a field of astronomy or astrophysics, you will definitely come across theories like this. Another application is in the navigation world, so calculating bearings. So if you ever have a flight or a ship that is carrying cargo and they need to now plan a route to a destination, right? We have our normal compass, which has the northeast, southwest directions, right? Northeast, southwest. Northeast, southwest. I think I've got that right. That's a compass, yeah. And if you want to measure, let's say between north and east, northeast, right? We can construct a 90-degree angle here, and we can create what we call vectors, which you'll learn in physics, right? Vectors are something that have both magnitude and direction, right? And we can actually use trigonometry, the basic ratios, to work out the distances to travel along those routes. Another example was in building constructions, like I mentioned earlier in the start. The ancient Egyptians made use of trigonometry, the basic trig ratios, in fact, to help construct their pyramids. Okay, so there's just a small list of some of the applications, but the one I really want to talk about, which I think is a very nice and fun one, sorry, is video games. Okay, so I know there's a cliche with mathematicians being like very awkward, introverted people, and yeah, I'm a bit introverted, I would say, but I love video games. Okay, and when you actually create video game characters and things and objects inside a game, you want to be able to tell how those objects move inside the game. So if you ever go into programming or coding, which is becoming more and more important nowadays in the fourth industrial revolution, knowing how to code and program is going to be a valuable skill. But not just knowing how to program and code, but understanding mathematics behind it helps you even more. Because that's how video games are created. There's mathematics inside the coding there. And trigonometry plays a big role in the code. So let's say you want to program a video game and you want to get the positions and speeds of an object by using x and y coordinates in the Cartesian plane, because that's how you map out your world, right? Your world is mapped out in a plane, okay? So to find the speed and position requires us to use right angle triangles, which we'll see. And therefore, that's why it's crucial to know trigonometry, right? And how to correctly use sine, cos, and tan in your code. So let's say we want to make a video game with a spaceship that wants to move from one position to another. Okay, we can model it as follows. So imagine here you've got your spaceship, okay? And it's now, let's say, orbiting a planet or something, okay? And you want your spaceship, which is starting off here, to move to a direction in your video game. Let's call it over here. Now, how do you tell your computer program, right? How do you code it to say, hey, I want you to move to that location in space, okay? So on the Cartesian plane, what's going to happen is you could say, for example, your spaceship starts on the origin 0, 0 on your Cartesian plane, and now you want to move it along an orbit in your video game. How do you find the new x, y coordinates to get to that position? So how do you tell the program, hey, from 0, 0, I want you to move to this point x, y, and that'll be the movement in your video game. Well, if we can say, well, let's move it by an angle of theta degrees, okay, we can work out the positions x and y now using trig. Because remember, sine of theta in this case is opposite, which is your, in this case, the x value here, divided by your hypotenuse, which in this case is the y value here. Okay? So in order to get your x coordinate by itself, I should rather call this r. Okay? Let's call this r for the radius. So we keep x and y as the positions in space. So let's call that r, because that's what we're used to doing, right? That's the radius r. Okay? So if I wanted to find the x coordinate by itself, then I could multiply both sides by that radius r. So r times sine theta equals x. Now I know if I want to move to a position, right, x, all I need to know is the radius length that it's moving, and you can program that in. So let's say you wanted to move along a radius of 1, and you wanted to move 30 degrees. Okay, well, we know radius is 1 and sine of 30 degrees is a half. So half times 1 is just a half. So you can tell your program to start at 0 and then move to a half, okay, in your video game. Then for finding the y-coordinate, I could say, well, this is the adjacent side here. So I could use cos of theta, right, which is adjacent y over the hypotenuse r. And again, if I wanted to solve y by itself, I'll multiply both sides by r. And now, again, if my radius is 1 and I've moved 30 degrees, my y value is going to be 1 times cos of 30, which is root 3 over 2. So that's going to give you root 3 over 2 as your y-coordinate. So now you can tell your video game, as you're programming it, the spaceship moves from here, 0, 0 in your origin, to the point a half root 3 over 2. And the only way your code can recognize that is by writing your code as, define your x-coordinate as r times sine theta, and define your y-coordinate as r times cos theta. And then in your code, you'll have your little text boxes for r and theta. And as you change those values, right, your spaceship will then start to move around in orbit. And that's how they actually make every single object and character that you've ever played in a video game move. Okay, so I thought that was just a little cool example to show you where trigonometry is actually used. It's used in a lot of places, and you'll see it pop up in your mathematics a lot. All right, okay, so we conclude this first half here with just that foundational building. Thank you so much for listening to me and just mumble on about maths. So I just love doing that. I'm now going to just hand over to my colleague Dan, and we will get started on some trig functions.
Hello everyone, I am Dan. Very glad to have you guys all over here, and I'm sure you guys had a fun time with Fabian. So now we're just going to go a little bit further and take this into the next gear and try to start graphing all of these functions. And just like Fabian said, you're going to see trig pretty much everywhere. I know I did my degree in biomedical engineering, and let me just tell you, whether you're going into any sort of STEM field or not, as long as there is some sort of force somewhere or some physics involved somewhere, you're going to see trig. It's extremely foundational, almost as much as algebra is. So you're going to see both of them quite often as long as you're going into some sort of science field. So in any case, let's continue going. And okay, so we're going to start with the unit circle. Now, when we're using this, I think you went over a little bit of this with Fabian before. You use a circle with a set radius of 1 to generate the right angle triangles. And we're going to take a look at how this looks like for each one of the trig functions that we have for sine, cosine, and tangent. And what we'll do is we'll see how the circle will then generate the sine wave function by plotting down the ratios of the opposite side to the length of the radius. So the first thing is you'll see that we have this table of all of these different ranges, and we'll have x and f of x. X would be what your degree measurement will be, and f of x represents what the actual value will be. So Fabian went over which quadrants will have positive values and which quadrants will have negative values. And as you can see in the table here, in the first and the second quadrants, you have everything that's positive. Because as we said before, sine represents your y value. And because it's representing your y value, anything that is above the x-axis is going to be positive. Anything below the x-axis, which would be quadrants 3 and 4, is going to be negative. So let us take a look at how this looks like when we are actually putting this on a graph. So over here, the first thing is we want to take a look at our unit circle. So if we take this and we put it at 0 degrees, we see that we're only at 1, 0. And right now for this, we're only going to look at our y values, because again, this is our sine. So if we go over to 30 degrees, which is one of our angles that our special angles, we can see that this is now at a half. So this is again was something that you guys went over with Fabian, but now you can actually visualize it and see how this works. So if we go again to 45, what do you guys think this will get to? Well, lo and behold, it gets to, this is really hard to get to 1 degree. Come on, okay. Okay, well, it gets really, really close. We'll have to just accept it at 46, I think, right now. It's just going between 44 and 46. It's not being very nice, but this will essentially give you your root 2 over 2. Now, if we go over to 60 degrees, remember, as we were doing our stuff before, this is now our root 3 over 2. So now you've seen all of the different special angles and what their y values correlate to on the unit circle. And the unit circle is so important because this is where all of that stuff comes from. It's extremely helpful because of the exact property that your radius is 1. And because your radius is 1, it gives you all of the ratios that you need. So now let's take a look at how it looks like when we do an animation for the sine wave. So as our A is being plotted, we can see the circle is going around, but as the circle is going around, it's plotting your y values. So you see that red line? That is directly relating the value on the circle to the value of your sine graph. And you can see as you go from 0 to pi, and right now these are all in radians. So let us just switch a little bit so that this is in degrees. So pi would be 180. Pi over 2 is 90. 2 pi is 360. 3 pi over 2 is 270, and so on and so on. So once we get to 4 pi, this is 720. This is 540. And then they just increase by 90 each time as we go along here. So 540 and 630. So you can see the nice sine graph that this makes just by going around the circle. And all of these values just correlate straight to what the value is on that unit circle as it's going around. Okay? Thank you. Now, let us go back a little bit and we will take a look at, so we went through all of these values here. Now, the main thing is when you're looking at this, and we showed before on the graph, we also need to know what the domain and the range of everything is going to be. So the domain of this is going to be all real numbers, because as you saw, it took on any x value. Our range only went from -1 to +1 on the unit circle. So those are the two key things that you guys are going to have to memorize for this. And you'll see a lot of similarities between sine and cosine. So just make sure to keep that in mind. So again, this is going through your negative values, and as you can see again, anything that is in the first and second quadrants are positive, anything that's in the third and fourth quadrants are negative. But we have these special values of 1/2, root 2 over 2, and root 3 over 2 that are just sort of repeated over and over again, either in positives or negatives. Okay, so those are, once you know those key values, you'll just see them over and over and over and over again, and you'll understand where all this stuff comes from. So now that we've seen the sine wave, you can show that you have an amplitude of 1. Now, an amplitude is how high and how low your wave goes, but it's only half of that. So we know that we went from -1 to +1, so that's actually going by 2. But we take half of it to find the amplitude, which is why our amplitude is just 1. And we saw that we start at 0, and it traces along that nice curve, and our period is 360 degrees because that's the exact degrees in a circle. So we said before that we were talking about the domain, and we said that the domain for all of these functions are going to be the set of all real numbers. But if we're looking at just one period, which would be one complete circle, it would be from 0 to 360 degrees. We also talked about our range, which went from -1 to +1, and we talked about our period, which is 360 degrees, which was for the circle. And then our amplitude, as we said before, was 1 because it's half of the max and the min of our y values. So now we're going to take a look at the effect of different variables within our sine function. Now there's a lot. There's a, there's b, there's p, and there's q. So we're going to take a look at each one and kind of drill down to what they actually mean. Now pay very, very close attention because I want you guys to see a pattern here. You're going to see the same things for sine, for cosine, and for tangent. So make sure that you see that they all do the same thing for all three of the functions, okay? We're still going to go over them so you can see what happens to them, how they change it, and everything, but just make sure you realize that they do the same thing. So as long as you know what they do for one of them, you know what they do for the others, okay? So A is going to be in front of our sine, and this one will either compress or stretch our graph. And I'll show you this in just a second. But what this essentially means is that if A is greater than 1, your function will be stretched. And if your A is between 0 and 1, your function will be compressed. Now, what happens when your A is negative? Well, it's going to do the same thing with stretching and compressing, except now it's going to be reflected about the x-axis. Now, what does that mean? That essentially means you take a mirror, you place it straight on the x-axis, and that's your new function. That's what reflecting means, okay? So let us take a look and see how this stuff looks like. So if we go to our sine graph over here, we're only changing our A value. So what happens when, let's zoom out just a little bit, and let us also erase some of that stuff. So what happens when your A changes? So watch as the A increases. Do you see how your function is now stretching and getting taller and taller? When our A is 2, now we go up to a maximum of 2 and to a minimum of -2. And as your A gets larger and larger, it just keeps going further and further up. So our amplitude here is increasing, and so is our range. Now what happens when it's between 0 and 1? We said it would compress. So watch what happens. Remember, green is our reference graph. So our red one now gets smaller and smaller in our amplitude and our height. And see, as it goes towards 0, it just makes a straight line. Now what happens when it reflects or when it gets negative? You can see the green over there, and let's go to -1, so it'll be perfectly reflected. Now, this is what we mean by you can take a mirror, put it on the x-axis, and you'll see your new function. This is exactly what reflecting means. So you can see that it's just an exact replica of your green graph, except it's mirrored. Now, we also showed before, if it's between 0 and -1, it compresses, just like it did when we were in the positive zone of 0 to 1. And then if we go even more negative, you can see that it also stretches. But again, this is just reflected and stretched. Okay? So that is what the A value does. So let us take a look, and okay, we did that. Now let's look at Q. So see how Q is on the end. This is going to be very, very key. You want to make sure that you know where each one of these values go. So A is in front of your trig function. Q is all the way at the end, all the way by itself. Now, if you remember stuff about your linear graphs, do you remember what your y equals mx plus b formula did? If you do, you'll remember what your b does. Your b is going to be doing the same thing as your q here. It's going to do a vertical shift. If your q is positive, you will be shifting upwards by q units. And if your q is negative, you will shift down by q units. So this just moves your graph up and down. That's really all it does. Okay? So let us take a look again and see what that does on our graph. So we are taking a look at our Q. So green is our reference graph. Now look what happens when we move our Q in the positive direction. So if we move this to +1, we can see the entire graph shifted up by 1 unit. And as we keep increasing Q, it just keeps shifting up further and further and further until it just goes way out of our graph. Now we can come back. So what happens when it gets negative? If you said that it's going to go downwards, you're exactly right. And you can see it just shifts downward by the exact units that Q is. So this is the magic of Q. You don't really have to look at anything else in your function. You just know that it shifts it vertically by Q units. If Q is positive, it shifts up by Q units. If Q is negative, it shifts it down by Q units. Okay, so now let us take a look at what P does. So P is inside our trig function. So this one is kind of special because it's going to affect what happens with sine. So when we put P inside of our trig function, it's going to shift it horizontally. Now what does this mean? Now I want you guys to think about this. Whenever you're doing a trig function, let's say you had 30 degrees. You would have sine of 30 degrees. But when you put in a Q, or a P, sorry, this is actually changing that 30 degrees to something else. So if your P was now 15, now it's going to be sine of 45 degrees because you have the 30 plus the 15. So this is why P functions as a horizontal shift, because it's moving where you are on the x-axis. Okay, so let us take a look at what it actually does, but just keep in mind that if P is positive, your graph is going to be shifting to the left. And if your P is negative, your graph is going to be shifting to the right. And it's also very important that you realize that in this function, you have a sine x plus P. Okay, so as long as it says plus P and you know that your stuff is positive, you're shifting to the left. If it says plus P and it's negative, you're shifting it to the right. So just remember that you have a positive or an addition sign there. Okay, so let us look at our graph again and see what happens when we manipulate our P. So as we move it, now this is going to be very, very small because we're in degrees here. But as you can see, as we increase this, we are moving further and further to the left. So if we go to 45, do you see how our entire graph just shifted over to the left by 45 degrees? And if we go all the way to 90, look at this. The entire thing shifted over. But you're probably wondering, this looks kind of like one of the other graphs we saw. Well, it does, because this is actually your cosine graph. They're just phase shifted by 90 degrees. And so we'll get into that a little bit more, but you can see that this happens if we go to positive 90. Now what happens when we go negative? So let's go back to our base point at P equals 0. So now we're at our green graph, and now we're gonna manipulate it to the negative side. Remember, positive shifts it to the left, negative is gonna shift it to the right. So as we go to the right, we can see the entire thing moving over. Now what happens when we go to negative 90? This looks kind of like your cosine graph, but it's reflected. So this is kind of how you can see the relationships between sine and cosine. So if you shift your graph over by 90 degrees, you are actually using a cosine graph. If you shift it over by negative 90 degrees, you're using a reflected cosine graph. Okay? So let us put this back at 0, which was our baseline, and then we can go back to our slides. So we went over A. Remember, A was our amplitude. It changes whether our graph is stretched or compressed, or where it is reflected. We went over Q, which moved us up and down vertically, or by that amount, and we just went over our P, which moves us either to the left or to the right. So we also said that there is going to be a B. So again, pay very, very close attention because B is inside of our trig function. Now B is tricky. It is a bit tricky because it's going to change a lot of things. But as long as you don't have anything else that's changed, B will tell you what your period is. Now remember, when we were doing this, we had a unit circle. So our sine was defined on a range of 0 to 360 degrees. So that was our period for 360. So if our B is positive, what you're going to find is that your new period is going to be 360 degrees divided by B. Okay? So let's say that your B was 2. If your B is 2, you have 360 divided by 2, and that gives us 180. So now what's really happening is you're completing your entire thing in less time. So you complete your full wave in less than 360 degrees. What happens if your b is between 0 and 1? Well, in that case, you're dividing by a fraction. But you should know that when you divide anything by a fraction, it becomes larger. So if we have 360 divided by 1/2, as we went over earlier with Fabian, when you divide by a fraction, you multiply by its reciprocal. So this becomes 360 times 2/1, which is 720. So now your full wave is taking 720 degrees rather than just your normal 360. Now what happens if b is negative? Well, it just gets reflected, but it does the same thing. If you're between 0 and -1, you are going to take more than 360 degrees to complete the wave. If you are more negative than -1, then you will take less time to complete your full period. Okay? But again, your period is going to be always defined by 360 divided by b. Just remember that when you're doing this, your period is always going to be a positive number. You can't have a negative period. Okay? So let us take a look now and see what this looks like on our graph. So we've done A, we've done P, we've done Q. Now we're on B. So as we can see, as our B gets larger, see how it starts shifting inwards? And if we go to 2, remember we said that we would have a period of 180 degrees. And that's exactly right. If you look at our red graph here, it starts at 0 and it reaches the same exact point all the way over at 180 degrees. So now you see if we go all the way to 360, where we would normally have 1 period, we've now completed 2 in our red graph. So that's how you can see that you now complete 2 periods in the time that it took you to do 1. And if we go smaller than 1, and in between, say, 0 and 1, let's go to 1/2. Now, we can't really see this. Let's zoom out a little bit. So if we zoom out, as we can see, you go from 0, and look at this red graph. We've already completed 1 period right there, and we've only gotten halfway. Now if we keep going, see how all the way over here at 720, we've completed 2 periods of our normal green sine function. But with our red one, because we have a b of 1/2, we are only completing 1 period. Okay, so this is why your period is going to be 360 divided by your b. Now, if we said that if it was negative, that it's going to be reflected. So let's take a look. Well, first, let's see what happens as our b gets smaller and smaller. Do you see how large this now gets? Let's see if we can zoom out a bit. Look at that. That's going massive. This is going all the way to 3,600 degrees. You've done 10 of your full periods of the green one. And now when we're at 0, it's just flat. But let's see what happens when we go negative. So let's go to -1, and we'll zoom back in. Remember, green is our reference graph, and red is now reflected. So if you remember, we did the same thing with our A, when our A was negative. So you can kind of see the correlation between the two. If your A is negative and your B is negative, what is going to happen? I don't know. Let's try to find out. Look at that. They're both negative, and they've canceled each other out because they've flipped themselves twice. It's like looking in a double mirror. You see yourself. So now you can see exactly what happens. So let's put this right back really quick. So A was 1. Whoa. That got way too big. Okay, so when our B is between 0 and 1, or 0 and -1, you can see that it starts getting compressed, or it starts stretching out along our period. So it starts getting longer and longer. And when our period, or when our B starts going into, or starts getting more and more negative, you can see that it starts doing the same thing that happened when we had our B being larger than 1, except now it's just reflected. So if we go to B of 2, you can see that we now, at 720, we now have 1, 2, two different periods of our function versus the other one. Okay? So, except now it's just reflected. So let's put this back at 1. Okay? And let us get back to our slides. So now we've gone over A, our B, our P, and our Q. So here's a quick question. What's going to happen if we have a B and a P? Because they're both inside our trig function. This could be a question that happens on your exam, and you kind of need to know this. Now, I'm asking this question because it doesn't do what you think it's going to do. It actually does something a lot different. So the best way to do this is so that we can show you. So actually, let's go back to our graph over here. So let's say that we have our P and we're putting this at 45. So if it's at 45, that means we are shifting our graph over 45 degrees to the left. But what happens when our B is now 2? As you can see, our graph hasn't shifted by 45 degrees anymore. It's something completely different. So let's do, there's markings on the graph at 30, so let's move this to 60. Do you see what happens here? Your graph is now starting, or where it would normally start, is at -30. So your horizontal shift is represented by your P over your B. So when we go back to this over here, we actually want to go a little bit up when we were talking about our B. So where were we talking about B? Where are you? Oh, P, sorry. So when P's are doing our shift over here, when we include B, your shift is actually going to be P over B. And that's when you have both of them, okay? So make sure to keep that in mind because, again, this is going to do the same thing for your cosine. So just as a quick review, we went over A, B, P, and Q. A was responsible for our graph being stretched or compressed or reflected. This is going to be the same thing for cosine, okay? Just letting you know. P is going to be responsible for our horizontal shift. And again, if you have a B, then your shift is going to be P over B. And again, same thing for cosine. Your Q is going to be responsible for your vertical shift. It's either going to go up or down. And your B is going to change your period, okay? And again, all of these are going to do the same exact thing for your cosine, and some of them are going to do pretty much the same thing for your tangent function, okay? So now let's go back and take a look at our unit circle. So if we take a look at our unit circle, remember sine was responsible for our y values. So as our A moved about, this is going super fast. Let's move it a little bit more manually. So as our A moves about the circle, you can see the different values in our y. That was our sine function. But now we're doing cosine. Cosine was our x. So if you look at our x over here, let's go back to 0. Our x at 0 is 1 because you're all the way over on the right-hand side of our unit circle. And when you see the cosine, you'll see that you start at 1. Now let's go to our 30 degrees, which was one of our key angles. And you can see here, remember our sine is our y, which is a half, and our cosine is 0.866, which is √3 over 2. And if we go to 45 degrees, which was the tricky one from last time, and it's still being a little bit tricky, that is √2 over 2. And if we go all the way up to 60, we think, because remember we have our √3 over 2, we have our √2 over 2, and we should have a half. So if we look, we can see that our y, or our x here for our cosine, is actually 1/2. And now let us take a look at what happens when we animate our cosine. So as you can see, let us take this all the way back so we can start in the beginning. So as you can see, now it is tracking your x value And you can see that it is going down and down and down. Now it's at 90 degrees and your x is 0. Now your x is going negative. That's why your graph is going below the x-axis right here. Once it gets all the way to the left-hand side, you're going to hit -1, which is, again, the minimum that you have here. And as you're going all the way to 270 degrees, you're going to hit 0 again. And then as you go to 360, you're returning back to your starting point. And this will be your complete period. So now we've known what our maximum is, which is where we started, right over here at 1. We know our minimum, which was when we got all the way to -1. And we can see that we're creating a period every 360 degrees. This is just like what we did with our sine function, except the starting points are different. And if you remember, they were phase shifted by 90 degrees. So we think that that should be the same thing for our cosine. And the same goes with what each one of our variables do. But let us just double check, because it's always good to check on the things that you do and make sure, okay? So the first thing is we just want to go over the different values. So as Fabian and you guys were talking about initially, when your x is in the first quadrant, it is positive. So you can see all the values from 0 to 90 degrees here are positive. But when your x is now in the second quadrant, that is not spelled part of your cast system. So you're negative in that area. So that is from 90 all the way to 180 degrees over there. When you get down into your third quadrant, again, you're in the negative value of your quadrants. So you're going to have negative values from 210 to 270 degrees. And now when you get into your fourth quadrant, this is where you had your C for your cast. So this means that you're positive in that quadrant. So from 300 degrees to 360 degrees, or actually from 270 to 360 degrees, you'll have positive values for your cosine. Okay? Now, if we do it the reverse way, if you go from negative 360 to 270, essentially all you're doing is you're going clockwise now instead of going counterclockwise. So you're still in the fourth quadrant here, so everything is positive. If you go into the third quadrant from negative 270 to negative 180, you're negative. If you're in the second quadrant from negative 180 to negative 90, you're negative again. And if you're in the first quadrant from negative 90 all the way to 0, then you are back in your first quadrant and everything is positive. And again, if you take a look here, you can see the same values being repeated. You have your negative a half, or your half, your root 2 over 2, and your root 3 over 2. And now these are just going to be repeated all the time, just like with your sine values. And as we showed when we were looking at the graph itself, we had a maximum of 1, and remember we started there, and then we had a minimum of -1. So this means that when we're calculating our amplitude, we're going to take the difference. So the difference between 1 and -1 is 2, because 1 minus -1, you're subtracting a negative, so it's adding a positive. So you have 2, and then you divide that by 2. So your amplitude is 1. Now, if we look at the domain, the range, the period, and the amplitude, you're going to see that all of this is the same exact thing as your sine function. So remember when we told you before that it's important to realize that a lot of these things are repeated? Well, this is exactly one of them. Your domain is also going to be pretty much all real values, but if you're just looking at your unit circle, it's going to be from 0 to 360 degrees. And because that's what it takes to go fully around your unit circle, that's going to be your period. Your range, as we saw when we graphed it, went from -1 to 1. And our amplitude that we just calculated out 2 minutes ago was 1. Okay? Now, let us take a look at what each one of the variables do. Now, I'm going to give you a second or two as I say what they are, because I want you to say, even though I can't hear you, I want you to say what you think A does. Okay? So what do you think A does? I'll give you a hint. It does the same thing that it did for sine. If you said that it stretched or compressed your graph, you are correct. And if you said that it also reflects when it's negative, you're 100% correct and you get a gold star. I don't have one on me. Wait, you can draw one. That's for you, okay? So If your a is positive and it's greater than 1, your function gets stretched. If your a is between 0 and 1, your function gets compressed. If it's between 0 and -1, it gets compressed and reflected. And if your a is less than -1, it gets stretched and reflected. So let us take a look at our graphs over here. So this was our sine graph. Let us now go to our cosine graph. So we are messing with a this time. So if our a is larger than 1, you can see it increasing. And if we go to 2 really quickly, we can see that our amplitude, or our maximum, goes to 2 and our minimum goes to -2. This means our amplitude is 2. Now just think about that real quick. See how that variable is a and your amplitude, they both start with a and they're the same values. A is 2, your amplitude is 2. So just when you're thinking real, or when you have your exam and you're taking these questions, they ask you about your amplitude, look at your a, okay? Now if a goes even further, you can see it stretches way out of the screen. Now what happens when it gets between 0 and 1? We said that it would compress. So we can see our red graph now getting compressed smaller and smaller and smaller, which is exactly what it did in our sine graph. And if we go negative, what do you think is going to happen? It's going to be reflected. And as long as we're between 0 and -1, it's still going to be compressed. And if we go to -1, we can see that it is perfectly reflected about our x-axis. Almost like we just put a mirror down right there. Now if we go even more negative, you will see that it gets stretched even more. So if we go to -2, we can see that it looked almost exactly like the same thing of when we're at a of 2, except now it's reflected about the x-axis. Okay? So let's put this back to normal, which was our 1, and let us go back to our slides. So we've done a. Q was the next one. So once again, I'm going to give you a few seconds. I'm going to ask you what it does, and then you're going to answer out loud to yourself or silently, up to you. If there's a lot of people, I know it could be kind of embarrassing just shouting out what this does. They might ask you some questions, so don't worry. So what does Q do to your trig function? If you said that oh wait, it's right on the screen. What am I doing? If you said that it shifts your graph vertically up or down, then you are 100% correct. Next time I'm going to ask this before we get to that slide. So, as we've shown before, if your Q is positive, it'll shift it up by Q units. If your Q is negative, it'll shift it down by Q units. Okay, so let us take a look at what that actually looks like on our graph. So, remember Q, our guy over here, if we move to the positive side, you can see him shift the red graph straight up. And if we move to 1, it moves the entire thing up by 1 unit. If we go further, you can see the entire graph just going further and further up, all the way into the sky. Now if we bring them back down, all the way down to where we began, and if we go negative, it should start shifting downwards. So you can see him going a little bit down here. If we go to -1, you can see him exactly 1 unit away from our green graph. And if we go even more negative, you can see it go all the way until it just is like a escalator out of the picture. And now we can bring him back. So normally our Q would be 0, but remember that if your Q is positive, your graph shifts up. If your Q is negative, your graph shifts down. So now we go to P. Okay, I caught myself this time. What do you think P does? And again, I'm going to give you a few seconds, and then let me know what you think it does, okay? Now, if you said that P is responsible for your horizontal shift, you are 100% correct. And if you said, wait, Mr. Dan, doesn't B do something to that too? You are even more correct, and you get 2 stars. This is like a Michelin rating. You can only get up to 3, so hold on. So you have 2 stars now if you said that B also does or affects your horizontal shift. But right now we're just looking at P, okay? So in the same exact way that our P affected our sine graph and moved it to the left or to the right based off of what its value was, it does the same thing with cosine, okay? So if your P is greater than 0, your graph is going to be shifted to the left, and if your P is less than 0, your graph is going to be shifted to the right. Now, what was something that we discussed when we were looking at our graph? It was something where our sine looked very much like our cosine graph. What did we call that? If you said it was phase shifted, you were 100% correct. Now, because our sine was phase shifted into being our cos, do you think the same thing can happen here? If you said yes, you were, again, 100% correct. Because look, once we do this, look at what we have. It looks very, very close to it, but it's not the same yet, is it? No. So what happens when we go negative? Now, this looks like our sine graph. So as you can see, in order for our cosine graph to turn into a sine graph, you have to have your P of negative 90. Okay? And remember, negative values of P, move your graph to the right-hand side. Positive values of P, move your graph to the left-hand side. Okay? Now let's put them back right into there. And we were talking about what happens when you have a P and a B. So remember, I think one of you, I don't remember who because I can't really hear, I'm just going off of telepathy right now, but somebody said that when you have a P and a B, that it affects your horizontal shift. So let's see what happens. If we move this to 90 and we have a B of 2, we said that our horizontal shift should be P over B. So that means that it should only shift by 45 degrees. So let's see what happens. If we move this to 2, you can see that the graph has shifted. Wait. Yes, okay. So the graph has shifted. And so when we go back this way at 0, this is what it normally looks like. And when we go all the way to 45 or 90, see, it's kind of hard to look with 90. Let's go to 60 because then everything's on the 30-degree marks that are on our graph. So now you can see things a little bit more clear, sort of. Not really, but it's moved only by 30 degrees. Trust me on this. It is a little bit hard to visualize sometimes, but the way to see this now is when it's at 90, see how it's right at the origin? And your green graph, when it's at 90, it hits the origin at this, or it hits the x-axis at the same point. That's how you know that it's shifted over, okay? So let us go back to our slides. So now we're looking at B, just B alone. And we said that B is responsible for our period. So our period is represented by what? Does anybody remember how to calculate our period? You said it was 360 over B. You are correct. And remember, this does the same thing with our sine function. And I'm saying that so often because it is so key that you guys realize that your A, your B, your P, and your Q do the same thing. So as long as you memorize one of them, you can memorize what they do for all of them, okay? So when our B is between 0 and 1, it's going to make our function take longer than 360 degrees to complete a period. If our B is greater than 1, it's going to complete your period in less than 360 degrees. If your B is negative, then it's going to take longer to complete the 360 degrees as well, and it should be reflected. And if your B is less than -1, it'll still take longer, or it'll take less than 360 degrees to complete a full period. So let's take a look at our graph. And let's see, we can move our P down to 0. Come on, there we go. Okay, so for our B, we're going to put them at 1 because that's where we start off, and we're going to just zoom out a little bit. So first things first, we're going to go between 0 and 1. So if we do that, we should see it taking longer than 360 degrees to complete a period. And as you can see by our graph right now, in our red, once we go all the way back up to 1, we're at 720 degrees. So our green graph has completed 2 full periods at that point. Now if our B goes more than 1, so it's now at 2, and this we're probably going to have to zoom in a little bit, we can see that it's done 1 full period in 180 degrees. And if we go all the way to 360, it does 2 periods in the same time that it took our regular graph to do 1. Now, let us go negative. So if we go down, bam. And now we go to -1. So I was wrong. It doesn't shift or it doesn't reflect about the x-axis. That was my bad. It stays exactly the same. Okay? So if it goes to 0 or between 0 and -1, it's going to do the same exact thing that it did when it was between 0 and +1. You can see that the period just increases. Now if we go more negative and we go all the way past -1, it's going to do the same thing that it did when it was super positive or greater than 1. It's going to make your period take less time than 360 degrees. So again, you can see that now when it's at 2, it's completing 2 full periods in the same time it takes your graph to complete 1 originally. Okay, so now we can put this back to 1. So we're back to our regular stuff, and we go back to our slides. So again, we've done our A, our B, our P, and our Q. So what do they all do? You said A is responsible for your stretching or compressing and reflecting about the x-axis, you are 100% correct. If you said B tells you what your period is going to be and tells you whether it's going to take longer or shorter than 360 degrees to complete 1 full period, you are also correct. If you said P is responsible for your horizontal shift, you are correct. And if you said that Q is responsible for your vertical shift, then you are also correct. So remember, Q is vertical, B is your period, A is your amplitude, and P is your horizontal shift. Unathi, I think you had a question, is that correct? If you do, or if it was just a mistake by raising your hand, that's fine. But if not, you can always raise your hand and then we can see what's up. Okay? So, now we move on to our tan function. And if you remember when you were talking with Fabian, your tan function is going to be identified by sine divided by cos. And what you're going to see is now you have something on the bottom of your fraction. What happens when that is 0? You get something that is undefined. And you'll see what exactly happens when we go through these tables and when we look at the graph itself. So as you can see on the table right here at 90 degrees, at 90 degrees you have a cos of 0. So that means that your tan function is undefined. And if you remember from the values that you guys were calculating out with Fabian, at 0 it's 0, at 30 degrees it's √3/3, at 45 it's 1, and at 60 degrees it is √3. And if you also remember, you have your cast functions. So when you're in the first quadrant, everything is positive. When you're in the second quadrant, this is going to be negative. When you're in the third quadrant, it is going to be positive. And when you're in the fourth quadrant, it's going to be negative. Just remember, cast starts all the way down in the fourth, and then it moves around. Okay? And then if you go in the reverse direction, it just does, you have the same exact values, except now you're going from the 1, 2, 3. Oh, okay. So now you're in the third quadrant and then you go around that way. Okay. So let us take a look at what the function looks like when we are graphing it on our unit circle. Now, you're not going to really be able to see what the values are, but you can see that you're going to have your cosine over your sine. And you can take a look at some of these values, and you can know that when you're at, let's see, when your A is at 90 degrees, you can see that you're going to have a sine of 1 and a cosine of 0. So this is right where you're going to have an undefined function. And if you see, you can notice that you're going to have the same thing when it reflects about the x-axis. And that is when you're at 270 degrees. So now you know that when you're at 90 or 270, you're going to have an undefined function. Now those are important values because as you're going to see in a little bit, there's a pattern to this, okay? And if we go all the way over to 180, your sine is now 0. So this means that your tan function is going to be 0. And if you start out at 0, your sine function is also 0 again because you have a y of 0. So your tan function is also going to be 0. And then anytime that you get to 45 degrees or a multiple of 45, you're going to have either 1 or negative 1, okay? So let us take a look at our graph of the tan function. Now this looks kind of crazy, doesn't it? It looks nothing like the ones that we've done before. You're probably thinking, what is this? How am I ever going to make sense of this? But don't worry. It just looks like this. It's a little bit scary just to look at, but we'll make sense of it in a second, okay? So you remember that when we were at 0, your sine is 0. So that's why right over there at the origin, you're at 0 degrees. And we also said that when you're at 90 or 100 or no, 270 or negative 90, your function is undefined. So what this means is that you now have two asymptotes. These are points where your graph cannot touch. It cannot go beyond those lines right there, okay? So as we said before, it's very important that you see that there's a pattern to this because it's going to happen every 180 degree multiples of where your asymptotes are, okay? And that's why you can see the blue lines kind of just spread out like that. There can be more. The thing is, Desmos doesn't really let you propagate these to infinity, so you have to kind of like put each one in. So that's why we only had a few of them. But let us take a look at some of the properties of our tan function. So here you can see the graph that we had before, and it looks exactly the same thing. The only thing is here you don't have the asymptotes. But you know that anytime that you get to 90 or negative 90, and then any multiple of 180 beyond those points, you will have an asymptote, okay? So the way to kind of write this is to say 90 plus 180n. And that's what it means by 180 degree multiple. You can also do negative 90 plus 180n. And it's going to be the same thing. It's kind of just like if you put n as negative 1. Okay? So these are going to be where your asymptotes are. Now it's going to be extremely important when you're graphing this stuff to graph your asymptotes, because then you know exactly where your tan function is going to be. So if you draw a line straight down here and you draw a line straight down there, you know it's got to be in between there. Okay? So now, because it has asymptotes, it's not going to have the same domain as your sine and your cosine. So what does that mean? Well, as we can see here, it's going to be the set of all real numbers except for those asymptotic values. So we said before that it's going to be 90 plus k, or n, times 180 degrees. And that's going to be everywhere that you get your asymptote. But everything else is fair game for tangent, okay? Now your asymptotes, as we said, they're undefined over there because your cosine is 0 at those values. When your sine is 0, that's fine. That just means your tan is 0. Okay? Now your range, if you remember from looking at these graphs, see those blue arrows right there? That means that you go all the way to positive infinity and negative infinity along your y's. So that means that your range is going to be from negative infinity to positive infinity. And your period, remember how we said that there is a pattern to them and how it's between negative 90 and 90? Well, that's 180 degrees. So that means that your period is going to be 180 degrees. And that's exactly why your asymptotes are at every 180 degree multiple. Okay? So now you're probably wondering, how does that work when we have our A, our B, our P, and our Q? Well, if you look at what we say here, it's doing the exact same thing with A. Remember, our A stretches or compresses things, and it reflects things about the x-axis. It does the same thing here. I know you thought that tan function looks completely different, and you thought maybe this stuff has like a little trick up its sleeve. But no, it does the same exact thing. Okay? So when your a is greater than 1, it's going to be stretched. When your a is between 0 and 1, it's going to be compressed. And when your a is between 0 and -1, it's going to be compressed and reflected. And then when your a is less than -1, it's going to be stretched and reflected. So let us take a look at our graphs. And we can see what happens as we change our a. So remember, these green lines are our function. So we want to see how those change. So if we change our a so that it becomes larger, do you see how it becomes stretched? It's kind of like you took the two ends and you just pulled at them. Now what happens when we put our a between 0 and 1? As you can see, it gets compressed. It's kind of like you're taking those two ends and you're pressing them down so it kind of flattens out near the axis. And then when you're at 0, or go to the negative side, you see how it flipped so suddenly? That is because your a is negative. And if you go to -1, it's completely reflected about the x-axis. And once again, if you're between 0 and -1, it's compressing. If you're more negative, it gets stretched. Okay? Until it looks almost like a line. That's kind of crazy. So let's put this back to 1 and go back to our slides. So what does Q do? Now remember, Q does the same thing here that it does in your cosine and your sine function. Q is responsible for your vertical shift. So it's going to tell you if your function is moving up or down by Q units. So let us take a look at what that looks like on our graph. If we take Q and we increase it, see how if we go to 2, now our function intercepts the y-axis at 2 instead of 0. And when we go negative, it's going to move the entire thing downwards. So if we go to -2, you can see it intersecting the y-axis at -2. Okay, so if we put this back. So when we are with P does our horizontal shift. So remember, for our sine and our cosine, it did the same thing. It just moves your graph to the left or to the right. So here, if your P is positive, it's going to move it to the left, just like it did with sine and cosine. And if your P is negative, it's going to shift it to the right, just like it did with sine and cosine. So let's take a look at our graph. And we are manipulating P. Do you see how it's just sliding over like that? Now don't pay any attention to the blue asymptotes. So now we're just taking a look at our red graph. You can see it's sliding over. But what does that mean about our asymptotes? Our asymptotes are going to move with it. So as your function moves over by that amount, your asymptotes are now, they're not going to be at 90 and -90, they're going to be at 45. So you have to remember that as you move your function, your asymptotes move with them. Okay? And if you go all the way to the left or at 90, you can see now your asymptote's going to be right at the y-axis. And we can see as we move it so that P is negative, it does the same thing. Okay? So let's put this back to 0 and go back to our slides. So what does B do? Now remember, B does our period. So when your B is between 0 and 1, it's going to complete your wave in longer than 180 degrees. If your B is greater than 1, it's going to take your period less than 180 degrees. If your B is between 0 and -1, it's going to take longer than 180 degrees to complete the wave. And if your B is less than -1, it's going to complete it in less than 180 degrees. So same exact stuff that happened with your sine and your cosine. Okay? So let us take a look and see how that affects it. So for our B, see how they are now getting closer and closer. Now you have way more of these red lines together than you did for your green lines. And you can see when we go to 2, now you actually have one in the middle of your green lines here. So now you have 1, 2, 3 of these, or actually 4 if you count where the or where the other one would have been. So as you go between 0 and 1, you can see that they are now going to take much longer to complete a period. And if we zoom out, you can see just how many of your normal tangent lines you had to use in order to complete one period of your red graphs. And when it goes to 0, it flattens out, and when you go negative, it reflects about the axis, okay? And between 0 and -1, it is still increasing the period, and when you go beyond -1, it is making your period less than 180 degrees. Okay, so let us put this back to 1, which is where we were before, and we can go back to our slides. So now we're going to go through some examples together. So first thing before we do this is, whenever you guys are doing these examples or any homework problems or any exam problems, you have to remember your BODMAS. So it's BODMAS, okay? So what does that mean? That means that you have to obey that when you are looking at your functions. So the first thing is you want to look inside your parentheses. So find out what's happening there. Your B is going to be extremely important. So that should be one of the first things that you find out what it is, how it's going to change your graph. Then you have your P that is inside your trig function. Again, you need to know what that's going to do. And remember, if you have a B and a P, it's going to change things up from just the regular way. Then you can take a look at your A, which will determine your amplitude. And last, you can take a look at your Q, which is going to do your vertical shift. Okay, so let's take a look at this function here. Okay, so if we have, let's see, how do I go back to, okay, so if we go back to here, we have our function f of x equals 2 sine of 2x. So let's just write that right over here so we don't forget it. So we have 2 sine of 2x. So first things first, identify what your A is, your B, your P, and your Q. So whenever you have trig functions, just write these out. And one thing I always tell my students is the more things you write out, the less things you have to remember, the less things that can go wrong. The more things that you put pen to paper with, the more things that you just know is there, okay? So what is our A? Now, if you remember, A is in front of your trig function. So our A over here is 2. Now, what is our B? If you remember, B is in front of the x inside of the trig function. So our B here is also 2. Now, do we have a P or a Q? Well, there's no addition or subtraction within the trig function, so that means our P is 0. And there's nothing on the outside of it, so there's no shifting it in the vertical direction either. So we know that P and Q are responsible for our horizontal and our vertical shift. So that means that there's not going to be any shifting whatsoever. So our function is going to look kind of the way that it normally should. So we have a sine function, so it should look like this. And remember, no shifting, so that should start at the origin. Now we take a look at A. Or actually, we take a look at B. So B was our period. So we determined that our period was represented by 360 over B. For this, it's going to be 360 over 2, which is 180. So that means that our function is going to only take 180 degrees in order to complete one full cycle. And so on this graph, we can actually make anything represent what we want. So what we can do is all the way over here, we can say this is 360, and just about halfway, we'll say this is 180, okay? And then we'll put this right there, okay? Oh, okay. So if we look at our problem here, it actually states it just wants it on the domain of 0 to 180 degrees. That makes that pretty simple. So if we go back here, we don't really need some of these things here. So we just want the range 0 to 180. Wait, undo that. Okay. So if we go back to our pen, we want 180. We're just going to say this goes all the way out over there, okay? And what we're going to do is we're going to say that the top and the bottom is equal to 1 and -1, okay? So we know that our period is going to take the entire thing. Now, we also said that we have an A. Now our A is 2, so that means that where we put our 1 and -1 is not going to work. So that means we need to change these. So these need to be 2 and -2. So what's going to happen is our function is going to start right at the origin, because remember, there's no shifting. There's no P, there's no Q, so there's no horizontal or vertical shift. We have our B that's telling us that our new period is 180 degrees, and we have our A that tells us that we have our height of going up to 2 and to -2. So we have an amplitude of 2, okay? So if we put our 90 degrees here and say that this is 45 and say that this is 135. Now the reason we put those there is kind of important, because if you look at our graph here, there's 4 very distinct places in our graph, okay? There's the beginning, there's the end, there's the halfway point right there, and then there's the minimum and the maximum. I reversed those when I said them. The minimum is right down there, and our maximum is right over there, okay? So if we know this, that means we can kind of plot those points on the graph and then graph it. So we know that we start at 0, we know that we end at 0, and we know that halfway it's going to hit 0 again. And then we know that at 45 over here, it's going to hit our maximum, and then at 135, we're going to hit our minimum. So now it's just connecting the dots. And we've all done this since like first grade. So we go up, we come down, we hit that, and now we come up. And this is the graph of your function. So let us go back and take a look at the questions that were asked, because we need to see if it was even asked to draw this. It wasn't, but we just did it anyway. So that's a good thing, okay? Now we know how to graph it together. So let us take a look. Oh, but look here. What is the domain and the range? Graphing helps you find that. One thing is that it kind of told you what the domain is right here. So your domain is from 0 to 180 degrees. If we look at our graph, we can see that our range went from -2 to 2. So your range is from -2 to 2. Okay? Now what is the period of f? Now we calculated this together because of our b. Remember, our period is 360 over b. In this case, it was 360 over 2, which gave us 180 degrees. The amplitude, remember what we said, amplitude starts with A. Your variable A, they go together. A is your amplitude, so our A over here of 2, so our amplitude is 2. Now what are the x and y intercepts? So this is something where it makes it really nice to have the graph, because you can see exactly where it intercepts everything. So we can immediately see for the x-intercepts, it goes across it 3 times. We have 1 there, we have 1 there, and we have 1 there. And what do you know? This point right there is both your x and your y-intercept. Okay? So we have our, we can do this on the page over here. So we have intercepts at 0, 0, and this is for x and y. And then if we look here, we have one at 90 degrees. So then we have 90 and 0 for your x, we'll say x2, because it's the second x-intercept. And then for your third x-intercept, we have it at 180 degrees, comma 0. Okay, so these are the 3 different intercepts that you have for your x and your intercept for your y. Now it's asking you, what are the maximum and minimum turning points? So for this, we take a look back at our graph. Now, our maximum and our minimum are just the ones that are, as we said, our maximum and our minimum. And remember, we use these to graph our function. So our maximum is right over there, and our minimum is right over here. So remember, whenever we're stating what these points are, you have to have an x and a y. So this would be 45, comma 2, and this would be 135, comma negative 2. So if we go back, we have our maximum at 45 and 2, and our minimum at 135 and negative 2. So that's just a quick example of how you can solve for all of these things just by knowing what your A, your B, your P, and your Q do. Okay? Remember, A was your amplitude. It tells you whether your graph is stretched or compressed. Your B is responsible for your period. Your P is responsible for your horizontal shift. And your Q is responsible for your vertical shift. Your period is 360 over B, and you will need to see what happens with your B and your P if there's any problems like that to see if it changes your horizontal shift, okay? So now I'm going to change this over to Fabian, and he's going to help you with the next problem.
Cool. Thanks, Dan. Thanks for that explanation on the sine, cos, and tan graph and doing an example there. So I'm going to do an example here for you guys. And yeah, let's have a look at it. So we want to sketch the function g of x, and it's given by cos of x plus 60 degrees plus 2. So as Dan mentioned, when you look at your BODMAS, you need to look at those algebraic operations in their correct order in order to start sketching this graph. Okay, so what is BODMAS? Let's just remind ourselves algebraically. Okay, you look at brackets first, then you look for of, which means exponents. You look for divisions, multiplications, addition, and then subtraction. So in this expression here, in that function, the brackets first here inside has an x plus 60 degrees. So I know I need to do this transformation first. That's essentially what you're doing with your A, B, P, and Q values, those parameters there, and how Dan mentioned how they affect the graph. They're actually transforming your graph. Okay? So I do that operation first, then I see, is there any exponentiation? There's no of, there's no exponents here. Okay, trig becomes very scary when there's exponents. So we don't draw the exponential trig graphs. Division, there's no division here. There's no multiplication either. So division or multiplication will happen in front of your cos, right? So like your A value. Then addition, well, there's addition at the end there, plus 2. So just when you thought you got away from BODMAS in primary school, no, BODMAS is the universal standard language for algebra. I'm going to compose myself there. We're having too much of a good time here in the studio today. Okay, and they give us a domain, 0 degrees to 360 degrees. So already we've answered the first question here, and that's where we're going to draw the graph. So let's go ahead and just create a new Cartesian plane to get us going. So we know we want to go from 0 degrees, which is your origin, to 360 degrees. Okay. And again, let's see if I've got this right. 1, 2, 3, 3, 6, 9, 12, 18, 2, 4, 7, 3. Yeah, I'm going very granular on this. So each tick that I've got here is 30 degrees. So 30, I know it's a bit small, but just every tick there, every one block unit is 30 degrees. So 30, 60, 90, 120, 150, 180. We generally use 30 degrees as the most minimum intervals when we draw, just because it's the first special angle we learned, and it's the smallest special angle that we learned. So we can put down the values quite easily. So 270, 300, 330, and 360. So let's just get the graph up here. So g of x is cos of x plus 60. So let's write it up here. G of x equals cos of x plus 60 degrees plus 2. Okay, so just as Dan mentioned, let's write out our parameter values. Okay, most information that we can have is always the best. I can guarantee you from over the years of helping students, almost 100% of the time when you can't answer something is because you haven't written down all the information that you have. Okay, so list out all that information. Your A value, which goes in front of your trig ratio cos, is just 1 here in front of that. So your amplitude A is 1. Okay, so we expect the graph to have an amplitude of 1 when we sketch it. The next value is B. Now if I look in front of my x, there's no value in front of the x, but there's a 1 in front of there. Okay, because it's 1 times x, which is x. So your B is 1. So therefore, when you calculate your new period, okay, you take the original period of your, what I call the parent graph, right? So cos x, which was 360 degrees. We divide it by that B value of 1. So the period will still stay the same, 360 degrees when you draw this G of x graph. The P value, now we've got a P value inside the bracket here, and it's plus 60 degrees. Okay, so that means it's going to move, the entire cos graph is going to move 60 degrees to the left. Now, because I'm anticipating that happening, I'm going to be a bit smart here. I'm going to draw negative 30, negative 60, negative 90. I don't have to go more than that, but I'll go negative 30, negative 60, negative 90, because that's where the graph would originally start. But remember, you were given a restricted domain of your graph to be from 0 degrees to 360 degrees. So when you actually draw your graph, you're only going to start from 0. We'll see what it looks like when it actually moves 60 degrees to the left. There'll be a little bit of chunk left over. But when we draw the graph, we draw it in this domain, 0 to 360 degrees. Then lastly, a Q value, that value I've got outside here is plus 2. And remembering what Dan said, that is a vertical shift of 2 units upwards. Okay, so if we have just a rough sketch, remembering that cos of x has this sort of shape here, from 0 degrees to 360 degrees. And it's got 2 x-intercepts here, and it's got a minimum turning point here, a maximum turning point here, and a maximum turning point here. So that's at 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. The amplitude of that graph, original cos x graph, was 1, so that's not going to change. The period's not going to change either. But now the P value, which is 60 degrees, means that this original graph is probably going to shift over 60 degrees to the left. Okay, so it'll probably start here, left, come down like that. I'm just drawing very rough sketch in green right now. Okay, but this is what we expect the graph to sort of look like. Okay, when it's shifted 60 degrees to the left. And then lastly, it has another transformation where it's moved up by 2 units. So from that green graph, we expect that entire graph to move up by 2 units, and it'll probably look something like that. So that's just like a very rough sketch of it. But we're going to go plot the points now and see how that works. So I like to show every single function and the transformation happening in real time, so you can kind of see, right? It's faster obviously to plot the points at the end, which is what you'll do, but I like to show you the visual transformations of what's happening to each graph. So I'm going to put my max at 1 over here. Okay, I'm anticipating that because the amplitude is 1. But then there's also Q. So now I almost got caught out, right? Because we know it's going to shift up 2 units. So because it's going to shift up 2 units, we probably expect the old maximum of 1 to be a maximum of 3. Okay, and we'll see that when we draw it. And then the old minimum was -1, but if I move that up 2 units, because the whole graph's moving up, then I probably expect the minimum to be at 1. Yeah, -1 plus 2 is 1. Okay, so let's draw the original cos graph first in orange. Okay, so originally it would start at 0, 1. It would go to 90 degrees 0. Then it would go 180 degrees -1. 270 degrees 0. And 360 degrees 1. So originally, my cos graph would look like this. Okay, I think Dan has won the artist award between the two of us for today's lesson. Okay, all right, so that's the orange graph. That's your original parent graph, cos x. Okay, so let me just note that, yeah. So I'm just showing you what each graph is looking like after we do each transformation with those a, b, p, and q values. Okay, the next transformation that we have to do first, according to BODMAS, is move the graph over 60 degrees to the left. So let's do that one in green. So what I do, because I'm only affecting the x values on this horizontal shift, my y values are staying the same. So I'm just going to take every single x value and just move it over 60 degrees to the left and keep the same y value. So from 0 degrees 1, if I move back 60, I go negative 60 degrees 1. From 90 degrees, if I move 60 backwards, that gives me a 30 degrees, and the y value is 0. At 180 degrees, right, if I move back 60, it's 120 degrees, and the y value is negative 1. 270, moving backwards 60 degrees is 210, and it was 0. And then lastly, 360, moving back 60 is 300, and it goes back to 1. So the graph of cos x plus 60 degrees is this one here. And you can see from the orange graph, you've just taken that exact same graph and you've just shifted it over everywhere to the left by 60 degrees. So that's cos of x plus 60 degrees. Then finally in blue, the final function, right, the last operation according to BODMAS means we must add this to that q value. So now the x values are not being affected, but your y values are now being adjusted vertically up by 2 because it's positive 2. So at negative 60 degrees 1, if I go up 2 units, should be negative 60 degrees 3, right? But notice I'm not going to draw it from there, because remember the blue graph is the final graph. That's your answer for sketching it. I'm not going to draw it because the graph actually starts in this domain here. So I'm just going to note it starts there. It would have started here if the full domain was from minus 60. At 30 degrees, it was 0, so it's going to move up 2, okay, and it's going to cut there. So because it starts at 0 degrees, I'm going to have to find that y value, okay, and we can actually do that quite nicely, right, because it's a function at the end of the day. That's the important part here when you do trig functions. Just because you're in the realm of trigonometry now, doesn't mean functions have suddenly disappeared, right? You still do the normal things you would do for functions in a trig function. So because at 0 degrees, how do I find the y value there? Well, in any function, you substitute that x value, 0 degrees, into your function. So I get cos of 0 degrees plus 60 degrees plus 2. Well, cos of 0 plus 60 is just cos of 60 degrees plus 2. And we know from our special angles, can you see why they are so important? They are just popping up everywhere. Cos of 60 was a half. So you have a half plus 2, which is 2.5. So that'll be up here. So that's where your graph is actually starting from. 0 degrees, 2.5. And I'm going to label that because it's quite important, right? That's a y-intercept, right? When your x value is 0. Okay, so coming back to the green graph now. At 180 degrees, it is negative 1. So if I shift that up entirely by 2, I should get 180 degrees and 1. At 210 degrees, it was 0. So if I shift that up by 2, I should get 210 degrees 2. And then at 300 degrees, it was 1. If I shift that up by 2, it's going to be 300 degrees and 3. So if I sketch that graph now, it's looking like this. Okay, and that is the full graph drawn on that domain. But now can you see 360 degrees? We stopped at 300. So we need a value for 330 and for 360. Okay, so let's go find those two values, substitute them in, and then we will finish completing the graph. Okay, so at g of 330 degrees, remember I substitute that into the function. So that's cos of 330 plus 60 is 390 degrees plus 2. Okay, so now we can pull up the calculator, pop that in, see what we get. Cos of 390, I'm using the calculator because it's not a special angle at the moment, but I could reduce it if I wanted to. But let's just use the calculator. And I get cos of 390 plus 2 is 2.866, which is very close to 3. So it's up here somewhere, or down there somewhere. And then lastly, at 360 degrees, it's going to be 360 plus 60, which is 420 plus 2. That's going to give me 2.5. So at 360 degrees, I get a y value of 2.5. Now that is the fully completed function for g of x. Okay. Doing all of that, I want to now show you how you can check that you've drawn your graph correctly. And even if you weren't able to plot point by point like this is the way now you can draw any trig graph. Not just any trig graph, any function you wanted to. So on your calculator, you'll click mode and you'll see table. So I click 7 for table. I put in my function as I see it. Cos alpha x, so the x is above that little bracket, plus 60, and then close brackets, and then plus 2. Okay, there's no second function g of x that I want to add. Now, where do I start? Well, I start where my domain says I'm going to start, at 0 degrees. I then go up to where it ends, at 360 degrees. How many steps do I want to take? What are the intervals? Well, we worked in 30-degree intervals, so let's put 30. Now, look how nice that is. It gives you a table format to plot your points, if you weren't sure how to put it into the trig function. But we should be able to. So at 0 degrees, you expect a y value of 2.5. That's what we got in the blue graph. At 30 degrees, it was 2. We worked that out. At 60 degrees, it's 1.5. And you can see our drawing wasn't so bad. It's around there, 1.5. 90 degrees, it's supposed to be 1.33. Yeah, it's like a 1/3, 1 1/3 almost. Or under 1 1/3. But it's over there. 120 degrees 1, we've got that on our blue graph. 150 degrees, you can sort of see like a symmetry coming out turning points, right? It's getting the same y values after the turning point. So 150 degrees, 1.13. 180 degrees, 1.5. Yeah, drawing's pretty good. 210 degrees is at 2, we've got that. 240 degrees, 2.5. Yeah, nice. 270 degrees, yeah, 2.86, very close to 3. At 300 degrees on our graph, we did have 3. At 330, we came back down to 2.8. And then at 360, we get 2.5. So that's how you can plot your points using your calculator, right, from a trig graph. And that's the best and fastest way to do it after you've checked your A, B, P, and Q values. Right, so you know you're guaranteed you're not going to make any mistakes. Okay, now that we've drawn that, let's just end off by answering the questions that was on that slide there. Okay, domain and range. Well, we worked out the domain. It's 0 to 360 degrees. The range, okay, of f. Okay, so let's go back there. Can you see? Oh, that's Dan's graph. There we go. So the lowest point here is at 1. Okay, because nowhere else on your y-axis is there a blue part of the graph. So your range starts at 1. And then it keeps going all the way up until it hits a maximum of 3. And then after 3, there's nothing left of your blue graph. So your range is from 1 to 3, including those values. Okay, next question. What is the period of G? Well, remember, period is 360 degrees for cos and sine. And we divide it by that B value. But the B value here was 1. So the period is still 360 degrees. Amplitude. You look at the A value in front of your cos. Our A value was 1. So your amplitude is 1. And you can see that on the graph that we've drawn here. The distance between the highest and the lowest points. Right? So 3 and 1. That's a distance of 2. And if you half it, you have 1. That's your amplitude. What are the x and y intercepts? Okay, that's very nice. There's only one intercept, which is the y-intercept. If we look at the graph, at 0 degrees, 2.5, because it doesn't cut the x-axis anywhere else. So it's at 0 degrees, 2.5. And what are the maximum minimum turning points? Well, if we look at the graph, the minimum one is here. At 120 degrees, it was 1. And at 300 degrees, it was 3. So the minimum turning point was at 120 degrees and 1. And the maximum turning point was at 300 degrees and 3. All right. And we're going to continue doing some more trig function examples. Okay, so the first one we have here is we need to sketch the function h of x which is represented by tan of x minus 30 degrees minus 1. Okay, so that's the function. And they've given us a domain to draw on from negative 90 degrees to 90 degrees. Okay, so the first thing I want to quickly look at is the function and just talk about those parameter values. So the a, b, p, and q. So a is the number in front of your trig ratio. In this case, it's a 1. So a equals 1. So that just means that the graph is going to have the same shape as the parent graph tan x. So there's no stretch, vertical stretch here because a equals 1. So the graph will have the same shape as the normal tan x graph. That's why it's important to know those parent functions, sine x, cos x, and tan x by itself. Next, I look in front of my x and I see that there's also a 1 here. So that means the b is 1. So remember, your new period of your h of x graph here is the old period of the normal tan graph, which is 180 degrees, divided by that b value, the positive b value, which is 1. So the period here still remains the same. The tan graph will complete one full wave in 180 degrees for this function. My p value here, so remember, we always have it as h of x equals, you have the a value, your tan of x plus p degrees plus q. So because it's plus p here and there's a minus 30, that means my p is minus 30 degrees here. So remember what this means. That means this is a horizontal shift by 30 degrees. And because it's negative, it's to the right. And then q, remember, is the vertical shift. In our case, our q here is minus 1. So this is a vertical shift by 1 unit. And because it's negative, it's going downwards. Okay. Now that we have the parameter values and what they do, we can now sketch the graph in that given domain. So let's do that. So it was from negative 90 to 90 degrees. So let's do some markings here. 30, 60, 90. Negative 30, negative 60, negative 90. Okay. So now that I've got my values on here, I'm just going to write out the function. Then I like to do each transformation so I can see what's happening to the original parent function at each step. So I use BODMAS again to dictate where I look in. So remember BODMAS. So brackets, so I'll start with the brackets and I see there's an x minus 30 degrees there. So that means the original tan x graph is going to shift 30 degrees horizontally to the right. So what I'm going to first do for the normal tan x graph, let's draw it in green. We know that there are vertical asymptotes at 90 degrees and negative 90 degrees, right? They're always spaced out 180 degrees because of the period of tan. Okay, and then the normal tan graph goes like this. So it approaches negative infinity from the left there, cuts the origin, and then goes up again. So between negative 90 and 90 degrees, this graph I've drawn here in green, that's the original tan x graph. That's the parent graph. So in blue, let's see what happens when we just move 30 degrees to the right. So tan of x minus 30 degrees. Now remember, these are affecting all your x values. So everything on your x-axis is going to shift 30 degrees to the right. So my asymptotes are also going to shift 30 degrees to the right. So at 90 degrees, the new asymptote will be at 120 degrees because everything on the x-axis is shifted 30 degrees to the right. Negative 90 degrees, the new asymptote will now be at negative 60. Okay. So now that we've got the asymptotes moved 30 degrees to the right, we move all the other values on that green graph to the right. So at 0 degrees, at 0, it now becomes 30 degrees, 0. Okay. At negative 30 degrees, you had a y value here. We can work it out. But now at 0, that'll have that value. At 30 degrees, you have a value over here on the green graph. So that moves over 30 degrees and that becomes 60 degrees with that same y value. At 90 degrees, there was an asymptote, but we already moved the asymptote over to 120. At 60 degrees on your green graph, it is over there. So at 90 degrees, it'll be over here. I'm just moving everything on the green graph by 30 degrees to the right. So that'll be there. Negative 90 degrees, they'll go to negative 60 degrees. So like a rough sketch right now for this graph would look like this. Okay, and your this should be approaching your asymptote, sorry. So let's go like that. This will be your asymptote here. Okay, but now we see that we've sort of got out of the domain that we started off with. So just remember the domain was from negative 90 degrees to 90 degrees. Okay. So we are now within negative 60 to 120 degrees according to this. We now need to get back to this original domain. So we still need to find out y values here from negative 90 to negative 60. And then we've already got up to 90 degrees here. Okay, so pull out the calculator quickly. So we can just pull out those other values for the for that graph there. Okay, so let's put in the graph. Tan alpha x minus 30 degrees minus 1. Okay, so let's put that in and put in those values. Okay, so I'm going to put in, so from negative 90, and I want to end at 90, and then the steps I'm taking are 30 degrees. Okay, so let's just have a quick look at those values. Okay, so at negative 90 degrees, it's 0.732. So that's going to be up here. So let's just label our values there. So that's 1, 2, 3 onwards. That'll be negative 1, negative 2, negative 3 onwards. Okay, so we saw that at negative 90 degrees, it was 0.732, which is roughly about here. At negative 60 degrees, we can see that the asymptote is now there, which is true. That's what we've drawn in blue there. At negative 30 degrees, we should have negative 2.732. So there's negative 30 degrees. Okay, so I've just drawn my y values a little bit off there. So let's just fix that up there. Okay, so this will be negative 2, negative 4, negative 6 rather. And then this here will be 2, 4, and 6. Okay, so at 30 degrees, or negative 30 degrees, it's negative 2.732, which is what we have here. Okay, so at negative 30 degrees, the associated y value here was negative 2.73. At 0 degrees, it is negative 1.57, which is over here. So at 0 degrees here, it is negative 1.57. I'm just realizing here. So the function we've drawn was already with the minus 1. Okay, so let me just take that away. Apologize there. Okay, so we're starting back at those same intervals again. Okay, so now it's 1.732, which is, yeah, that's what we have close there on our diagram. Okay, at negative 60 degrees, you still have your asymptotes. At negative 30 degrees, still negative 1.732. Now it's negative 1.732. Okay, apologize there. I put the wrong values in that calculator, so you just got to be careful when you put your values in. Notice what function you're using first. Okay, so let's just erase that over there. So at negative 30 degrees, we have negative 1.732. Okay, at 0 degrees, it's negative 0.57, which is over here. Negative 0.57. 30 degrees, it's 0. Okay, that's what we had on the original graph there. 60 degrees, it's 0.57. So I'm just labeling all the points on this blue graph here, tan of x minus 30 degrees first, because that's the first transformation that's happening. We're shifting everything 30 degrees to the right. So that's 0.57. At 90 degrees, it's 1.732. 1.73. Let's just round off the 2 decimal places. Okay, and that's where it stops. Okay, so we don't need this chunk here because on our domain we're drawing from negative 90 to 90. Okay, so from negative 90 it's 1.732, and it's going to go up and approach the asymptote here. Okay, so that's that blue graph tan of x minus 30 degrees in the domain negative 90 to 90 degrees. Lastly, in orange, we're going to do the vertical shift. Okay, so now we're going to look at the blue graph, and now we're going to shift that entire graph down by 1 unit. Okay, so the x values are now staying the same, and the y values are being adjusted. Okay, so remembering here at negative 90 degrees on this blue graph, it is 1.73. Okay, so if I move down 1, it's going to start here at negative 90 degrees and 0.73. Okay, so I just moved 1 unit down. So it'll approach the asymptote like that now. From negative 60 degrees, okay, so it is still approaching the asymptote. At negative 30 degrees, it is negative 1.73. So if I move 1 unit down, I'll go to negative 2.73. So let's put our dot there. At 0 degrees, you had negative 0.57. So if I move down, it'll be 0 degrees, negative 1.57. At 30 degrees, it was 0 on the blue graph. So if I move down 1, okay, then it should be 30 degrees and negative 1. And so on. You keep moving all these y values downwards by 1. Okay, and then we connect the graph. So it should look like this here. Okay, and it stops at 90 degrees here. So at 90 degrees, it'll be 0.73, right? Because we've just shifted this blue one down by 1 unit. So let's go ahead on the calculator and now just verify that we've done the graph correctly. So we put in the final graph. Okay, so tan of x minus 30 minus 1. We start at negative 90, end at 90, and we go in 30 degrees. So at negative 90 degrees, we have 0.73, which is what we have on the orange graph. At negative 60 degrees, you can still see it's in the asymptote. So the graph's still going to approach the asymptote from either side there. At negative 30 degrees, we now have negative 2.73, which is what we have on the graph. At 0 degrees, we have negative 1.57, which is what we have. At 30 degrees, we have negative 1. That's what we have. 60 degrees, yeah, it's just moved down by 1. Okay, so it's negative 4.2. And 90 degrees is now 0.73, which we have here. Okay, so the graph in orange is the final resultant graph. Okay, so the ones in green and blue are just the transformations. I started off with the original tan x graph. I then shifted it 30 degrees to the right to give me the blue graph. And then I shifted vertically 1 down to give me the final graph, which is an orange there. Okay, so let's have a look at what the questions were asking here. Find the domain and range of h. Okay, so the domain, they gave us the restricted domain here from negative 90 degrees to 90 degrees. So that's your domain. So your domain of your function h is from negative 90 degrees to 90 degrees. What's the range of your function h? Well, if I go back to that graph, I can see that this asymptote here at negative 60 degrees, it's going all the way down to negative infinity. And although it stops here at 0.73 at 90 degrees, on the left-hand side of the graph, can you see it starts up at 0.73 again on the y-axis, and it goes all the way up to infinity. So the range here is still from negative infinity to positive infinity. Okay, and open brackets because you don't include infinities. What is the period of h? Well, we work that out, okay, because our b value is 1. So the period of h is still 180 degrees. And then for c, what are the x and y intercepts? So let's go back to the graph. Looking at the graph, I only see 2 intercepts. Okay, so I see a y-intercept here at 0 degrees, and it'll be negative 1.57. So let's put that in. So the y-intercept is at 0 degrees and negative 1.57. Okay, and then the x-intercept I see is here at 60 degrees. At 60 degrees, is it 60 degrees? No, that was 0.53 something. So it's actually just a bit more than 60 degrees. So if you draw your graph and now you've only got it in the 30-degree intervals and you can't see on your graph what's the x-intercept, okay? We have to solve this algebraically. So you can see your algebra still pops up in your trigonometry. So how do I do that? So let's create a new page and then we can work it out. So remember, in any function, not just in trig functions, if you ever want to find the x-intercept of any function, you set y equals to 0. Okay? Our function was y equals tan of x minus 30 degrees minus 1. Okay, so if I set that equals to 0, I have 0 equals tan x minus 30 degrees minus 1. Okay, so I need to solve for x by itself. That's the goal. So I'm going to add 1 to both sides. So I'm going to have tan of x minus 30 degrees equals positive 1. Okay, so now how do I get x minus 30 degrees by itself? Well, you have tan as a function on here. So we apply the tan inverse on both sides. Okay, and you'll see this on your calculator. Just above tan is, you can see a tan inverse button. So the tan and tan inverse here are going to cancel each other out. We're going to have x minus 30 degrees. And the tan inverse of 1, I can work out quite quickly. I can say it's 45 degrees, and you'll ask yourself, how do you get that very quickly? Okay, well, remember the special angle diagrams, okay, when you had 45 degrees, and 90, it was 1, 1, and root 2. Well, tan of 45 degrees is opposite, which is 1, over adjacent, which is 1. So the tan of 45 degrees equals 1. So if I take tan inverse on both sides, I should get tan inverse 1 equals 45 degrees. But we can just check that to make sure that we're right. Okay. So if I go shift tan inverse of 1, I get 45 degrees. Okay. And now to solve for x by itself, there's negative 30 degrees on that side. So I need to add 30 degrees on both sides. And now I get x equals 75 degrees. Okay, and that'll be your x-intercept right over here. And you can see it's just past 60 degrees. Okay, so my x-intercept is at 75 degrees, 0. And again, if you put into your calculator 75 degrees for x here, so tan of 75 degrees minus 30 degrees minus 1, you should get 0 because that's what the x-intercept means. Your y value becomes 0. So if I plug that in, I do see I get 0. So it is correct. Okay, so that's answering the x and y intercepts for the tan graph here. Let's have a look at this one. So here we want to sketch the function f of x is 3 times sine of x plus 30 degrees on the domain 0 to 360 degrees. Again, I look at my parameter values, so my a, b, p, and q. I see the a, so that's the number in front of sine, which is 3. Okay, then I look at b, that's the value in front of x, it's just 1. I look at my p, so it's in the form x plus p, so my p here is 30 degrees. And I look at q, well, there's no number outside the sine function, so it's 0. So let's recall what these parameters do. Well, a equals 3 means there's going to be a vertical stretch. Stretch. I think I spelled that a bit wrong there. Yeah. Let's put the erase there. A vertical stretch by 3 units. Okay. So whatever your original sine x graph will look like. So remembering the original shape of the sine x graph, which looks like that, from 0 to 360, it just means there's going to be a vertical stretch now by 3 units. Okay. B equals 1. So remember, for your new period, it's the original period of your sine x graph, which is 360 degrees, divided by the positive value here, but 1's already positive, so it's fine. So 360 degrees will be the period of this function f. The p value is plus 30 degrees. So let's remind us what that does. That's a horizontal shift by 30 degrees. Because it's positive, it's to the left. And q equals 0 means that we don't shift the graph up or down vertically. Okay, so let's go ahead and sketch this graph. Okay, so it's set from 0 to 360 degrees. Okay, so let's put 360 degrees over here. Okay, and then each interval will be 30 degrees. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and 36. Okay, so each tick there is 30 degrees. Okay, and I'll be a bit smart now, because remember that the A is not just a vertical stretch for sine and cos, it's also the amplitude. Okay, and it's always the positive number. So positive 3, that'll be the amplitude. So we actually know the max and min value of this function is going to go up to 3. So I'm going to put 1, 2, 3 over here. -1, -2, -3. So let's just write the function here. F of x is equal to 3 times sine of x plus 30 degrees. Okay, and that's between 0 degrees and 360 degrees. That's the function we need to sketch. Yeah. Okay, so let's draw the original sine x graph in blue first. Okay, so original sine x, so at 90 degrees it's 1, at 0 degrees it's 0. So just remembering my special angles, that's how I'm constructing the graph. 30 degrees it's half, at 60 degrees it's root 3 over 2. Okay, at 120 it's still root 3 over 2. At 150 it's a half, 180 it's 0, and so on. And then you go there, so that's 210, 240, 270, 300, 330, and 360. So that's the original graph sine x in blue here. Okay, so it's very important. That's why we spent so much time yesterday drawing those parent functions and explaining how they are constructed, because you need to know how to draw them very, very well. Okay, so that blue graph there is sine x. Okay, now BODMAS tells me to look at the brackets first, and I see I have to do a 30 degrees shift to the left. So in green, let's do that. So y equals sine of x plus 30 degrees. Okay, so everything's going to move over 30 degrees to the left. So negative 30 degrees, it'll start here at 0 now. Now I'm not going to sketch that part of the graph because I'm still focused on my domain here that they told us to draw within. Then 30 degrees, if I move that to the left, will now become 0 degrees, and that had an original y value of a half. So I'm just taking every single x value here on the x-axis, I'm moving it 30 degrees to the left, but I'm keeping the y values the same. Okay, so I'm just moving each one over by 30 degrees. So let's keep doing that there, that shifts over there, that shifts over there. So this graph in green here now is the sine of x plus 30 degrees graph. And you can see from the blue graph, it's just moved over to the left by 30 degrees. Okay, so it ends at 330 degrees, but we still need a value for 360 degrees. So I'm not supposed to draw that part there. Okay, it starts here at 0 degrees. So how do I get what the 360 degrees value is going to be here? Well, let's just go ahead on the calculator and plug in. So remember, it's sine, I'm looking at the green graph, of 360 plus 30 degrees. So I've just put x equals 360 degrees there so I can just get the coordinate. And I get a half. So at 360 degrees, it's a half. So the graph continues upwards there. Okay, so from 0 degrees here to 360 degrees, this green graph represents sine of x plus 30 degrees inside the domain 0 to 360. And last in orange, we're going to do the final transformation, which is 3 times sine of x plus 30 degrees. So that 3 means it's a vertical stretch by 3. So all the y values are being affected, but the x values are staying the same now. So at 0 degrees, you had a half. If you multiply that by 3, so half times 3 is 1.5. So it should start over there. Okay, and then every y value you see, on the green graph is just now being multiplied by a factor of 3. So that would have been root 3 over 2. If you multiply by 3, you'll be roughly somewhere up here. Then at 60 degrees 1, it'll now be 60 degrees 3, because you're multiplying everything by 3. And that's true for every single y value on the graph here. Well, 0 degrees here times 3 is still going to be 0. Sorry, 0 times 3 is still going to be 0. Okay, the green graph there, that becomes negative 1.5. So I'm just multiplying all my values by 3. Okay, if I do that, I should get a graph that looks like this in orange. So it starts at 0 degrees, goes up to the maximum of 3, turns there, comes down again, starts turning, reaches its minimum point here at negative 3, then turns back up again, goes up, and then reaches that 360 degrees point there. So that's 360 degrees. The y value was a half originally, but now because we multiplied by 3, it's 1.5. At 330 degrees, it's still 0, because 0 times 3 is still 0. Okay, I'm just looking at the special values here. The turning point is going to be, this was 330, 300, 270. This was at 240 degrees, if I'm correct here. 180, 210. No, 270 degrees. Is it? 240 degrees. That's what it should be. We'll check on the calculator because that'll be the plotting for all the points. Okay, the x-intercept, so 3, 6, 9, 12, 150 degrees at 0. The maximum turning point here was at 60 degrees, and it was 3, and it started at 0 degrees and 1.5. Okay, so let's check. Plot our table. So mode table. Put 3 sine alpha x plus 30 degrees. Okay. I want to start at 0 degrees and end at 360 because that's the domain we were given. Okay, and then I'm going to move 30 degrees over. Okay, so at 0 degrees we have 1.5. We've got that drawn on our orange graph. 30 degrees, it's 2.59 or 2.6 if you round off, which is roughly what we have here on the orange graph. 60 degrees, 3, yeah, that's what we have. 90 degrees, it came back to that 2.6, which we have. 120 degrees, 1.5, we've got that. 150 degrees is 0, okay? So that's an x-intercept, right? Because we get a y value of 0. Just like 0 degrees, 1.5 will be our y-intercept. 180 degrees, which is over here, that gives you negative 1.5, we've got that. 210 degrees gives you negative 2.6, we've got that. 240 degrees, negative 3, we've got that, nice. That's going to be our minimum turning point. 270 degrees, negative 2.6, we've got that. At 300 degrees, we've got negative 1.5, we've got that. 330 degrees, we have 0, we've got that, so there's another x-intercept. And 360 degrees, 1.5. So perfect, we've drawn the graph 100% correct. Okay. So let's go answer the questions on that. Okay, so domain and range. Well, for domain, we were given the domain of the graph f. It's from 0 degrees to 360 degrees. And the range of the graph, well, let's go look at our graph that we drew. Okay, you see that it starts at the minimum value of negative 3. Okay, and it goes all the way up to your maximum point, which is 3. Okay, so your range is going to be between negative 3 and positive 3. Okay, so remember your range is all your y values. What's the period of f? Well, we worked that out, right? So the period is going to be 360 degrees because the b value was 1. What is the amplitude of f? Remember, amplitude is always that positive a value there because it's already positive. A is just equal to 3. That's the amplitude. What are the x and y intercepts? Okay, so let's go back to the graph to check that. The y-intercept was at 0 degrees, 1.5. So the y-intercept is at 0 degrees and 1.5. The x-intercepts, well, there was more than one. So let's check our graph. The first one was at 150 degrees and 0. So we plot that. And then the other one, so I'm going to write or, was at a 330 degrees and 0. So 330 degrees, 0. Okay, so those are all my x and y intercepts for that function. Lastly, it asks what are the maximum and minimum turning points. Well, you can see that your minimum turning point here is at 240 degrees and -3, and your maximum turning point is at 60 degrees and 3. So let's put that in. So for E, the minimum turning point was at, I just had it now, 240 degrees 3, -3. And your maximum turning point was at 60 degrees and +3. Okay, and that's answering that sign question. Let's have a look at this one here. So sketch the function f of x equals -2 times cos of x minus 60 degrees on the restricted domain from -180 to 180. So again, I examine my parameter values. So my a, b, p, and q. A was -2, okay. B, so the value in front of x is just 1. P, well, remember it's x plus p, so this p here is -60 degrees, and there's a no q value outside there, so it's 0. So let's remind ourselves, for A, because it's negative, okay, so first there's going to be a horizontal reflection, okay, so about the x-axis. So there's a mirror on the x-axis, as Dan mentioned. We flip the graph over that x-axis, and then we stretch the graph by a factor of 2. Moreover, because this is a sine or cos graph, that a value also represents your amplitude, and your amplitude will always be the positive number of that a, okay, because it's a distance. So amplitude here will be +2, and we'll see that when we sketch the graph. The b value being 1 just means that the new period is going to be 360 degrees for your cos graph divided by that positive b value, which is 1. So the new period will still be 360 degrees. So this cos graph that we have here, f, will still complete one full wave in 360 degrees. The p value -60 degrees just means that it's a horizontal shift to the right by 60 degrees. And the q value being 0 just means that there's no vertical shift up or down. So let's go ahead and draw that. Okay, so it's from -180 to 180. So let's put that there. 3, 6, 9. Okay, so if I put 180 degrees here, let's see what we measure our graphs in. Okay, so it's 180. So 3, 6, 9, 12, 50. Yeah, okay, so every 2 ticks, I'm going to call it as 30 degrees. 30, 60, 90, 120, 150, and 180. So it's still spread out by 30 degrees. And then the same thing here. Okay, so that'll be -30, -60, -90, -120, -150, and we just continue extending that line outwards there. Okay, so that'll be -180 degrees. Okay, so that's the restricted domain that I'm going to be drawing this function on. So f of x is equal to -2 cos of x minus 60 degrees. Let's check that there. -2 cos x minus 60 degrees, and that's between -180 and 180. Okay, so let's sketch those functions. So in blue, let's just draw the original parent function first. Y equals cos x. So again, because I know the amplitude is going to be 2 based off the a value there, I'm just going to be a bit smart, and I'm going to call that 1, I'm going to call that 2, I'm going to call that -1, that -2. Okay, so the original cos graph starts at 0 degrees 1. Okay, at 90 degrees it becomes 0, 30 degrees it was √3/2, 60 degrees it was a half. Okay, this is just your special angles again. At 120 degrees it is -√3/2, which is, 120 degrees it's a -1/2, right? So just remembering your values there. At 150 degrees it is -√3/2, and at 180 degrees it is -1. Okay, and the same thing happens on the negative side. So when you're in the negative quadrant, you're in quadrant 4, and with your cos diagram, those are going to be positive values for cos. So negative 30 degrees, it's still root 3 over 2. At 60 degrees, it's still a half. Negative 90 is 0. Negative 120 is still going to be negative a half. Negative 150 is still going to be negative root 3 over 2. And then negative 180 is still going to be negative 1. So in blue here, this graph I'm just drawing in dashed lines. That's the original parent function, cos x. Okay? And we're going to see how he transforms based off those parameter values. So that's y equals cos x. Okay, so if I use BODMAS, the next thing I must look for, after drawing the original cos graph, I see brackets first. So I need to do that part, and that's a vertical shift, okay, by 60 degrees to the right. So that just means everything on the graph is going to move over 60 degrees to the right. So negative 180 degrees, negative 1. If I move that 60 degrees over, it goes to negative 120 degrees, negative 1. Same for negative 150. If I move that 60 over, it goes to negative 90, negative root 3 over 2. Negative 120, if I move 60 over, it's going to go to negative 60, negative a half, and so on. Every single x value here on the degrees axis is just moving over 60 degrees to the right. At negative 30, that goes to 30 degrees, and that becomes root 3 over 2 again. Okay. At 0 degrees, move that over to 60 degrees, becomes 1. 30 moving over is 60. So that's there. 60 moving over 60. So that's over here. 90 moving over 60 is 150. 120 moving over 60 is 180. Now 150 moving over 60, right? That's going to go outside of our domain. So we don't worry about sketching that. So it goes like that. Okay, so you can see the green graph is just basically the blue graph just shifted over 60 degrees to the right. But I need values for negative 150 and negative 180. So again, I'll pop up my calculator and I'll just find out those values. Okay, so I'm looking at cos of x. So let's put negative 150 first. And then shift that over 60 degrees to the right, so minus 60. And I get negative root 3 over 2 for negative 150. So that'll be over here. And then for negative 180, if I go back and put that in, that's going to be negative a half, which is over here. So there's the graph. So it turns there and then comes back up. Okay, so this green graph here is y equals cos of x minus 60 degrees. Now the last graph in orange, which is going to be the final graph that we want to draw, is a negative 2 in front of there. So first of all, it reflects it over and then stretches it by 2. So from the green graph, how do we show that? Well, let's say at negative 180 degrees, it was a half. So first of all, negative half. So first of all, you'll flip it over the x-axis and it'll become negative 180 degrees, a half. And then you multiply by 2. Okay, so the negative sign means you flip it over first, so that's a reflection. And then you multiply by that a value, which is 2, or the value 2. So that becomes a half times 2 is 1. So negative 180 degrees, I should expect a y value of 1. Negative 150 degrees was negative root 3 over 2. If I flip that over, okay, it'll be positive root 3 over 2, which is somewhere up here. And then I multiply by 2, so it's just going to be positive root 3, which is somewhere up here. Okay. Then at negative 120 degrees on the green graph, it was negative 1. So if I flip that over, it goes to positive 1, and then I multiply by 2, so positive 2. Same thing with negative 90 degrees. It was negative root 3 over 2, so it'll end up flipping here. At negative 60 degrees, it was negative a half. So if I flip over first, then multiply by 2, I end up here. Negative 30 degrees, that was 0. So if I flip it over, it's still on 0. And if I times by 2, it's still 0. So that remains 0 there. This 0 degrees here, we don't know what that actually is, but we can work it out. So on the green graph, if you put 0 degrees here, you're going to have cos of negative 60 degrees. But that's in the fourth quadrant here, where cos is positive, negative 60 degrees. Okay, so it's equal to, well, cos of 60 degrees is a half. And because it's still in this cos positive quadrant, that value is a half there. So if I flip that half over, it now goes to negative a half. And then I multiply by 2, so it goes to negative 1. So that's where that green value flips over for 0 degrees. 30 degrees, it was root 3 over 2, so I flip it over, it goes to negative root 3 over 2, and then I multiply by 2, so negative root 3. And I just keep applying that same logic to every single x value. There it was at 1, I flip it over, it goes to minus 1. I multiply by 2, so minus 2. Same thing for 90 degrees, it ends up flipping here. At 120 degrees, it was a half, flip it over, it's a negative a half, multiply by 2, it's negative 1. 150 degrees is 0, so that's just going to remain on 0. And 180 degrees is at negative a half, so it ends up flipping to a half. Then multiplied by 2, it's equal to 1. So this is what the graph will look like now if I connect the dots. Okay, so go there, cut the x-axis negative 30 degrees. Okay, finds a turning point there, comes back up again. Okay, so let's label the important parts here. So the end points were negative 180 degrees, and that was positive 1. The turning point here was at 120 degrees, and it had a maximum turning point of 2 there. There's a x-intercept of negative 30 degrees and a y value of 0. There's a y-intercept, so at 0 degrees, we got minus 1. At 60 degrees, we have minus 2 as the minimum turning point. We have 150 degrees and 0 as another x-intercept. And the endpoint was 180 degrees and 1. So let's go ahead and check that these are right. So put out the calculator. So put on table. It's going to be negative 2 cos alpha x minus 60. Okay, I want to start from negative 180. And I want to go to 180. And I want to go in intervals of 30 degrees. So at negative 180 degrees, we have 1. That's what we had. At negative 120 degrees, we have positive 2. So I'm looking at the special points we labeled. We've got that correct. All right. At negative 60 degrees, it's 1. The graph was just sketched out a bit off there. But at negative 30 degrees, it's 0. I'm looking at the key points here. The x-intercepts, the y-intercepts, those turning points. At 0 degrees, we had negative 1. That's what we had on our orange graph. Okay, at 60 degrees, we have the minimum turning point of negative 2, which we have. Okay, 150 degrees, we have 0, so there's an x-intercept. And then at 180 degrees, the endpoint, we have 1. Okay, so we've got the graph correct. So let's go ahead and answer those questions on there. So what is the domain? We're given the domain of the graph, which was from negative 180 to 180 degrees. Okay. The range of the graph, well, let's go check. There's a minimum turning point there of negative 2, and it goes all the way up to a maximum turning point of 2. So my range is from negative 2 to positive 2. The period of the graph, we worked that out already. It's 360 degrees. Amplitude, remember, it's the positive value in front of there because it measures the distance. Okay, so look at my graph there. Okay, that amplitude is 2. Okay, so you can see there's the distance from the x-axis to that vertical crest. Okay, so that's a distance of 2. That's the amplitude. It's the maximum height that your graph has in this case. So it's either 2 down or 2 up there. But that distance is the amplitude. So the amplitude here is positive 2. D, what are the x and y intercepts? Okay, so the y-intercept is at 0 degrees, and we had minus 1. Let's check. Yeah. And then x-intercepts, I count 2 x-intercepts at negative 30 degrees and at 150 degrees. So the x-intercepts are at 30 degrees, negative 30 degrees, 0, or at 150 degrees and 0. Okay, so those were the x and y intercepts. And lastly, we're going to find the maximum minimum turning points. The maximum was at 120 degrees 2, and the minimum was at a 60 degrees negative 2. So let's put that in there. So the minimum turning point was at 60 degrees and negative 2. and the maximum turning point was at a negative 120 degrees, and it was positive 2. Okay, and that's what we can see. Where's that graph gone? There's there. Sorry, so that would be a negative 120 degrees there. Okay, so negative 120 degrees, positive 2, and 60 degrees, negative 2. Okay, so those will be the maximum and minimum turning points. All right, let's have a look at another one. Okay, so we want to sketch the function now negative tan x plus 2 on the domain 0 to 180 degrees. So again, I look at my a, b, p, and q values. So the a in front of tan x is negative 1. The b, there's nothing in front of the x, so it's a 1. P, there's nothing being added or subtracted after x in the brackets, so that's 0 degrees. And q is positive 2. So let's remind ourselves what each of these parameters do for tan. Okay, so tan, there was no amplitude. It only affected vertical shifts, vertical stretches, sorry. So the negative 1, first of all, the negative means a reflection about the x-axis, and the 1 just means that there's no stretch. Okay, so the shape should still be the same. It's just a reflection about the x-axis. The b equals 1, that'll help us find the new period. And remember, the original period of the tan graph is 180, so it differs from sine and cos. And you divide it by that positive 1, and your period is still 180 degrees for this graph. So the graph will still complete one full tan wave every 180 degrees. Then the p-value, 0 degrees, that means there's no horizontal shift on that graph, left or right. And then q equals 2 just means there's a vertical shift upwards by 2. So let's go ahead and sketch that. So it's from 0 to 180 degrees. So 30, 60, 90, 120, 150. So let's put that in. Okay, and then let's just draw a function here. F of x equals negative tan x plus 2. That was between 0 degrees and 180 degrees. Okay, so let's draw the original parent function tan x first in blue. So remembering that y equals tan x has asymptotes at 90 degrees. Okay, and negative 90 degrees, and then it's always 180 after. So the next one would be at 270. On the left here, it would be negative 90, negative 270. But because we're only interested between 0 and 180, there's only one asymptote here at 90 degrees. Okay, it started at 0 degrees and 0 at the origin. Okay, let's put the value 1 here, 2, 3, and onwards. Tan of 45 was the easiest special angle. It was 1. So 45 is about halfway between these two guys here. So it'll be over here. I just need at most 2 points to get the shape of the tan graph because it goes upwards like that. And then tan of 180 was 0. Tan of 135, as we saw, it was in the second quadrant, right? Looking at your cast diagram. So I'm just pulling special angles the whole time. So 135 degrees there means 45 degrees here. Okay, and because it's in the second quadrant, it's negative. So it'll be negative 1 here. Okay, so that's negative 1, negative 2. So at 135 degrees, it'll be negative 1. So I just need the shape of that original tan x graph. Okay, so that's the y equals tan x graph from 0 degrees to 180 degrees. So I look at BODMAS, and BODMAS will tell me what to draw next. Okay, there were no real brackets because the x of that tan x, there was nothing inside there that was happening to that x. So the next thing on BODMAS will be multiplication, which is this negative 1 here. So I need to do y equals negative tan x first. Okay, so that just means perfectly reflect your entire graph about the x-axis. So you just make all the y values negative of themselves. So at 0 degrees, the y value is 0, and negative 0 is still 0. Okay, at 45 degrees, you had positive 1. So if I flip that over, it's going to be negative 1. Okay, so the shape of the tan graph will go in this direction here. Okay, so it's a perfect reflection about the x-axis. And then 135 degrees, it is -1, so it'll be +1 now. And you'll see at 180 degrees, it is still 0. So now if I reflect it over the x-axis, it'll look something like that there. Okay. So that is the y equals -tan x graph. So all I've done is just perfectly reflected about the x-axis because of that -1. And lastly, in orange, we have to draw the -tan x plus 2. Okay, because that's addition that happens at the end of BODMAS. So the plus 2 means I just move that green graph everywhere up by 2 units. So at 0 degrees 0, it now goes 0 degrees 2. At 45 degrees, it is -1. So if I move up 2, it'll be 45 degrees 1. Okay, and it still approaches the asymptote. So now it'll look something like this. Okay, so you can see the green graph has just been vertically shifted upwards by 2 units for all the y values. And then for this green graph here, if I shift everything up by 2 units, or at 180 degrees 0, it'll go to 180 degrees 2. At 135, it is 1. So at 135, it'll be 3, and so on. So that green part of that graph there is also being shifted up by 2 units. And again, it'll still approach this vertical asymptote here at 90 degrees. So that vertical asymptote keeps going up and down. All right. So let's just label the important points here. At 0 degrees, it was 2. Okay, at 45 degrees, it is 1. So I'm looking at the orange graph. That's the final graph there. It does look like it's an x-intercept. It looks like it's between 60 and 90 degrees. So we can go and work that out, and we will. Okay, then it goes down to the asymptote. And then back here, it's approaching the asymptote after 90 degrees, but then it's coming downwards. At 135 degrees, we saw that it was equal to 3. Okay, and at 180 degrees, it was equal to, where's that? 2. Yeah, I've just drawn that a little bit off there. So let's just fix that over there. Okay, so I'm just going to label that point there at 2. Let's go back to the orange graph. So at 180 degrees, it was 2. Let's put it up there. There we go. That's better. Okay, and it's still approaching the asymptote. Okay. So I already know x and y intercepts are going to be asked. Okay, so let's just go back to the questions and see how they want us to answer them first. So the domain of your graph f was given as 0 degrees to 180 degrees. The range of your graph, let's have a look. Can you see it's going all the way to -infinity here as it approaches 90 degrees? And it does all go all the way back up to y value of 2. But it starts up at 2 again and goes all the way up to +infinity. So again, your range, as you would expect it in a tan graph, is from -infinity to +infinity. The period of f, well, we worked that out already. It was still 180 degrees. And you can see in this graph at 180 degrees, there is a full tan graph being happening. It's just that it's different chunks of the tan graph, but there's still a full wave happening between 0 degrees and 180 degrees. Okay, and then the x and y intercepts. So the y-intercept is always the easiest one first. So we go to the y-axis and we see there's only one there at 0 degrees, 2. The x-intercept, well, let's just look at our graph and see how many there are. I can only see 1. Okay, but it's between 60 and 90. How do I get that? Well, I have to solve it algebraically here. So remember, for an x-intercept, in any function, you set y equals to 0. So therefore, you have -tan x plus 2 equals 0. Okay, so the goal is to solve for x here. So I'll move the plus 2 over first. Gets -2. I'll then divide both sides by -1. And I get tan x equals, well, -2 divided by -1 is +2. And then I apply tan inverse to both sides. So x is equal to the tan inverse of 2. So if I do that on my calculator, I go shift tan for tan inverse of 2. And I get 63.43 degrees. And can you see that was part way between 60 and 90 degrees. Okay, so my graph is drawn correctly. So 63.43 degrees. 43 degrees. So that'll be your x-intercept. 63.43 degrees and y value of 0. Okay, and that's answering that tan x question. Okay, so that'll bring us to the end of this session. We hope that you've enjoyed the lesson today. And yeah, many more trig graphs are out there. So keep practicing. Make sure you follow the method.